Okay, we're now recording. We'll go from the current slide. While it's coming up, let me go over some announcements. I think I may have read the first two of them to you last time, but if not, did I read you about a job offer? Yeah or no? No, okay. It must have been, yeah, that's right. This came in yesterday, so you wouldn't have heard it. I don't know anything about this, okay? It came in our email. It's from a Jonathan Jefferson, and I don't know him personally, but at the bottom it says Coach Jefferson, Boston State Community College. So he must be one of the newer coaches here because I've heard most of their names before. I don't know who he is, but I assume it's legitimate. The job offer. The company name is No Kid Hungry, okay? The company description. No Kid Hungry is working to end child hunger in America today by ensuring that all children get the healthy food they need every day to thrive. Sounds good. Job title, Brand Ambassador. I don't know what it means. I know what an ambassador is, but what brand are they ambassadoring in? Is it No Kid Hungry or I don't know. So, job description. 2 bullets. First, send out the items through the mail to the list of orphanage homes that would be provided to you in your city. Okay? I don't know what items they're talking about. Is these food items or these publicity items? I don't know. Number 2, mailing out letters of invitation from us to other non-governmental organizations, NGOs, foundations, or businesses in your city. So that sounds like they're trying to drum up support, monetary support perhaps. Sounds okay. Interested candidates should contact Henry via email. Now that seems a little bizarre. I don't know who Henry is. And the email address that's listed here is an HS, which could be Henry something another, though probably not something another. And then 7 numerical digits that don't make a lot of sense to me, but anyway, they're there at gmail.com. So I assume it's a legitimate email address, so they should contact Henry via email. The weekly wages are $350. Frankly, to me, that sounds a little on the low side, but I don't know. I mean, that's, if it's a 5-hour day, this is $70 a day, 8-hour work day maybe. I don't know. Maybe it's good. Maybe it's a great salary. I don't know. Thank you. Looking forward to hearing from you, Coach Jefferson, Boston State Community College. Now, if anyone's looking for work, or you know someone who's looking for work, get the information, especially that web address and the email address. And any other thing else you want off of here, get it and pass it on to them because, I mean, it's a job, okay? And it sounds like a job that's doing some good stuff. Now, here's another email. It was sent Tuesday, but I didn't get it printed until yesterday morning. It's from the dean. And the subject is the SGA, the Student Government Association Student Drive, please support. It says, for Boston State faculty, staff, and students, please contribute to this important SGA drive. Thank you. And here's the blurb about the drive. Now, when I was on the Birmingham campus last Friday, I saw this on the wall and went over and took note of it and, acted on it this week. But I hadn't received anything in the email about it. It's sponsored by the Boston State Student Government Association and ambassadors, so 2 of our pretty important organizations on campus. It's the Personal Hygiene Drive. All donations will be distributed to local homeless shelters, and then right under there it says November 13th through 22nd, which is a little disturbing. Well, a little confusing Is that when they'll be delivered, or is that when we're collecting? If it's either one, tomorrow is the 22nd. So they sent this on the 19th, okay? They've been collecting since the 13th. What was the delay here? I don't know. But anyway, so you got till tomorrow to bring in the items. On donation drop-off, Birmingham campus, the Academic Success Building. Now, if y'all have been over there, that's that brand new, huge building. Somewhere in there is a drop-off. They don't say where in there, but I'm sure you can stop and ask somebody. Okay? If you can't, if they don't know where it is, ask them where the Student Government Association is. I'm sure they've got some space in that room, in that building. Now, this is the part that got a little testy this week. Bessemer campus, Student Activity Recreation Center. Now, if that's what I think it is, it's a room down there across from the cafeteria, right? Okay. I went down there Tuesday when I brought in some stuff. It was locked. Well, I had a 8:30 class, so I didn't have time to, went around trying to find someone who might know, couldn't find anyone, so I went on to class. After class, I went down there again. It was still locked. This time when I went looking for people, I found somebody, like Renee Herndon. She works a lot with student activities. So I asked her, she said, oh, we don't have a student activities coordinator on this campus anymore, so it's locked because there's no coordinator. I said, well then, where are we supposed to drop these off? Oh, I don't know, give them to me, I'll take them over. I said, well, no, I'm going over tomorrow. Duh, I was thinking it was Thursday, it was Tuesday. So I still got them in my office. I should have given them to her. Okay? So, if you brought them in, I don't know what to do with them on this campus. So, if you can, take them to the Birmingham campus. But you only got till tomorrow to do so, I guess. Recommended items: shampoo, conditioners, soap, shower gel, combs, brushes, tampons, pads, lotions, deodorant, baby wipes, hand sanitizer, and socks. Okay? Now, they don't list anything about dental on here, but there is a picture of the toothbrush and toothpaste. I just happen to have at the house an unopened box of toothpaste, you know, and the tubes in the bottom. And I thought, okay, I can bring that. So even though it wasn't on the list, I brought it. Hopefully it'll be okay. So, if you can, bring something tomorrow to the Birmingham campus. If you can only get it to this campus, see if you can get it to someone who can get it to the Birmingham campus. Now this came in today. It was in the mail. And it's a pretty important thing, and I'm recording, so I hope everybody will listen to it. This is from UAB. It's the 2020 Summer Research Experiences for Undergraduates. Now, if you're not familiar with these are things that a lot of the major universities in the U.S. have. It's sponsored by the National Science Foundation. They write grants, write proposals, and if the NSF funds them, then they offer these experiences for undergraduates. Probably over the next few months, if it's anything like past years, we'll probably see 3, 4, 5 of these, okay? This one's the first one I've seen this year from UAB. Dear colleague, we are now recruiting for our National Science Foundation, NSF, supported Research Experience for Undergraduate, REU program. Theirs runs from May 17th to July 24th. So it's about a 10-week program in the summer. Theirs is titled Experimental and Computational Materials Research. Our program is among the longest running NSF REU programs in the country. We offer a broad range of interdisciplinary materials research experiences to undergraduate students with diverse backgrounds in physics, chemistry, applied mathematics, and engineering. So we're doing a little physics now, we'll do a little chemistry. Hopefully you've had some math courses, And if any of your engineering majors, that might be something to consider. But notice it's materials research, so there's other areas, and I'll mention those as we get to them. The research projects include, but are not limited to, electronic materials. Okay, so if you deal with electronic materials, this may be of interest to you. Nanomaterials, that's stuff that deals with those super fine, incredibly small particles. Lasers and optical materials. Biosensors. So if you're into biology, especially biophysics or things like this, and biophysics is next. Biophysics and biomaterials, and computer modeling. So computer science majors, seems like they should have been included in the list up there. I'm sure they can. Okay? Scientific research projects are developed specifically for undergraduates by an interdisciplinary team consisting of science and engineering faculty at UAB. Please find the enclosed recruitment poster. Now, I had it up here, but then, or I had my work study student put it here, but then when I read this, I decided maybe it needs to go somewhere else. So I took it down and took it for them to put somewhere else that the person wasn't in today. It says, please find the enclosed recruitment poster for display in high traffic and accessible areas. This is neither very high traffic nor is it all that accessible. Okay? So I thought someplace down on the career information work bulletin boards or something might be better. Okay? Also note that the application can be submitted electronically via the website. And they list the website here. Feel free to come and copy this for yourself. Or, I'm sorry, I'm a dinosaur. Take a picture of it. Okay, of course. Our application deadline is March 15th, 2020. Good long ways away, but this is a great time to start the process. Right around the holidays, got plenty of time to work on it. Decisions will be made no later than April 15th, and that will be right around tax day. Okay. We would appreciate it if you would bring the summer research opportunity to the attention of qualified undergraduates at our institution. We are especially interested in receiving applications from qualified women and underrepresented minority candidates. So they'll accept all, but they are really looking because they get very few of them to apply. So please, if you are interested, consider it. If students have any questions about logistics, housing, or travel arrangements, they may contact, and her name's here, Ms. Charita Cadenhead, the program coordinator. She's got a phone number. She's got an email address. Thanks for your assistance in this important endeavor. Please display the REU poster at a site accessible to all undergraduate students in your department. Okay. The guy who sent this is from the Department of Physics, but like I said, it covers a huge range. Now, they didn't say anything about compensation. The ones I've seen in the past generally will house you. That's why they said this question about housing. They'll put you up in the dorms for no cost to you. And generally when you get in the dorms, you get a meal ticket. So you can eat at any of the approved eating facilities on campus. Okay, so that's pretty good. Most of the time, they also pay a stipend. Okay, it's probably not a huge amount, but they usually do pay a stipend. They also will cover travel expenses, one time there and one time back. This is people who are coming from out of state. That would be especially helpful there. If you are in the area and you don't want to live on campus, you probably aren't going to get anything for not living on campus. But if you wanted to live on campus, you could. But if you want to go home every weekend or more often than that, you could, but they only pay you one trip there and one trip back. So that would be on you, okay? Anything other than the first arrival and last exit. So, but usually they're great deals and great experiences. So take advantage of it if you're interested. All right. What are we going to be doing today? hopefully proceeding significantly through chapter 6. Okay? We may even finish chapter 6 today. We'll see. But hopefully we'll get far enough to, in fact, I think we probably already pretty close to being far enough to do today's lab. So 2.5 hours here, and then the last 2 hours in the lab. The lab is a 3-pager, but it goes pretty quickly, okay? So hopefully, I think most of you will feel fairly confident you'll get out before 7:45. So, but that's up to you. Yeah. So we are in chapter 6. The section in 6, I think, is 6.3, magnetism. But we're well along the way in magnetism, or at least got started in it, on page 158, and it's the source of magnetic fields. And that's our slide name as well. Okay. Now, I want to say something I think I've said before, and if I haven't, or if you haven't heard it, get it. The source of every magnetic field is moving charge. So you see, charges, electricity, magnetism, intertwined like crazy. Okay? The source of any magnetic field is a moving charge. Well, wait a minute. That piece of magnet that we might have, what charges are moving there? Well, if you remember, there are only 3 naturally occurring elements. What are they? Oh, how soon we forget. Iron. Cobalt. Well, it's half a dime. A nickel, yeah, right, okay. All right, nickel. Iron, nickel, and cobalt. Okay? Now, why only those 3? Well, I think I pointed out to you before, those 3 happen to lie right next to each other. There's iron, 26, cobalt, 27, nickel, 28. Right there together in the periodic table. One after another after another. None of the other 100 or so odd elements magnetic. Why? Well, okay, you say magnetic fields comes from moving charges. Hey, every element has electrons going around the nucleus. So why aren't they all magnetic? Well, that wouldn't be very exciting if they were, but they're not. Lots of things would be sticking to each other if they were, but they don't. And that's because the orbits, the spins, and everything else are random in all those others. But in iron and nickel and cobalt, the way the atoms are aligned with and the electron spins and everything else, they just happen to be every iron, nickel, and cobalt atom is a little magnet. Well, then why isn't every piece of iron magnetic? They're not. Okay? I have in my pocket here a needle that is not magnetic. Okay? I tested it, and it's not. But it's probably made mostly out of iron, even if Ryan did show up today. Okay? All right. Now, that's because all those iron, nickel, and cobalt atoms probably naturally arrange themselves in random order. So if this magnetic field is this way, one's this way, one's this way, one's that way, every other way, all the fields cancel out pretty much. Unless you folks who had 111, if you remember, because you have volcanic activity, and most of that magma that comes from near the center of the earth, down there deep into the earth, is mostly iron. And when it comes up and lays out in lava flows, if those flows happen to line up with the Earth's magnetic field, then most of those atoms line up in the Earth's magnetic field, and then when they harden, they're naturally magnetic. Most of the others that line up randomly, no, not magnetic. Can be made magnetic, but are not magnetic. So, what we're talking about, there are microscopic fields. The intrinsic spins of the subatomic particles, electrons and protons. Those are your two charged particles. Actually, they found some more in the nuclei, positrons and not neutrinos, they're neutral. But there are, but mostly electrons and protons. The way they revolve and spin, they create magnetic fields, microscopic magnetic fields. However, and the orbital motion of electrons in the atoms, that's the going around the thing. So the spinning of the electrons within their arrangement and also the moving around the nucleus. If the electrons are moving around absolutely randomly, no magnetic. Okay? Speaking of magnetic attraction, here's Frank and Logan. Okay. Logan's here. And Frank is here. Is the other one laying out today?
No, he's here.
Oh,
He's
okay.
finishing up the class.
He what?
He's finishing up an online class.
Oh, okay. All right. So, but iron, nickel, and cobalt just happen to have the arrangements so that every one of their atoms is actually a little magnet on the microscopic level. Now, how about the macroscopic fields? The things we look at and measure. Well, we have permanent magnets, which are, the most original ones of those are what we called earlier lodestone, or the mineral name is magnetite. Those are those that when they laid out from lava, they laid out in the direction of the Earth's magnetic field, and therefore the atoms align themselves with Earth's magnetic field. Those that went other ways, randomly distributed. So that's like permanent magnets. Well, we can also take, and we will do it in lab today, we'll take something that's not magnetic, but made out of magnetic material, if I can find it again, and then we'll make it a magnet. One of you will do that. Okay? Now, the Earth's a magnet. Okay? Why in the world is the Earth a magnet? What's the primary element in the Earth's, the whole Earth? Iron, you're absolutely right. Not on the surface. On the surface, iron is probably, what, 3 or 4? I don't remember. But in the whole Earth, iron wins big time. So we're mostly a big iron ball. Well, balls aren't usually magnets, are they? Well, we are spinning on an axis, aren't we? Okay? The outer part of the Earth, very thin outer part, is the crust. Okay? Then there's a thick part called the mantle. That's mostly iron. Okay? The crust is all sorts of stuff. Silicon, oxygen, those are the primary ones in the crust. Okay? The mantle is mostly iron, but it has other stuff too. Silicon as well. But then the outer core, just inside the mantle, the outer core is liquid. Okay, this liquid, when the Earth spins like this, of course the mantle spins with the Earth because it's solid. The liquid just sort of sloshes around in there and probably rubs where the mantle is rubbing against it. And it's probably not a smooth surface either. Jagged, ragged, that kind of stuff as it's spinning. So that's knocking off electrons, and those electrons start moving in eddy currents, you might say. Okay? Most rapid movement around the equator. Lesser movement near the poles. Okay? That's setting up a magnetic field pointing toward the poles. Okay? That's Earth's magnetic field. Electric currents create magnetic fields. If you have a long strip of wire with a DC current going through it, direct current, all the charges moving in the same direction. Let's just assume positive charges here. And it's a straight wire. And you can actually do this. Run it through poke it through a piece of paper, okay? And then connect it to a pretty strong battery, okay? And you don't have any resistor on it, so it's going to get hot pretty quickly. Excuse me. So you can't do it for very long. Run it through there, but before you connect it to the battery, sprinkle iron filings. We'll see some of those in the lab too. Just a small coat of iron filings there. Then turn on a pretty high voltage. And if you're lucky, you'll see those iron filings sort of forming concentric circles or forming a pattern there. That's because it produces a magnetic field. So a moving charge, that's electric current, produces a magnetic field. Now, why did I say DC? Why did I say battery? Okay. Let me go back and give you another hint. It's one of our infamous right-hand rules. If you point your thumb in the direction of the conventional current, that would be the direction positive charges moved if they moved, which they usually don't. But the conventional current, put your right thumb in that direction, in the direction of the current, okay? Then your fingers will point in the direction of the magnetic field, okay, of your right hand. So that's how they produce that. Now, I ask again, why direct current rather than alternating current? What do alternating current, what do the charges do in that? Like that. So the fields would be going, so you wouldn't measure any field in an alternating current, but you would in a direct current. Now, that's what I said. You need a lot of current, pretty strong battery, and it's going to heat up that wire pretty fast, so you can't measure it very long. But it does create one. Now, instead of iron filings, you could take a pretty sensitive compass and put it near that, and you'll see wherever you put it there, the compass is going to point the same direction your right fingers do. Okay? You can see that. Okay? Now, how can you enhance that? It's a very weak magnetic field. We'll take that wire, rather than running it straight like this, make a loop with it. Now, picture the current flowing like this, go up to the loop, okay? Depends on which way you want to do it, so I'm going to do it this way. Loop like this as I go around the loop. Notice my fingers are always staying inside the circle, pointing upward. So now they're reinforcing each other. So one loop makes a much stronger field than a single wire. And the single wire's field is this way, the loop's field is this way, Okay. Well, take that loop and make several loops. Make a coil. And when you make the coil, you get even more. Lots of reinforcement. In no time, in a little time, that electromagnet, one more thing to do. After you've got a coil of wire with a DC current running through it, okay, stick an iron core right down the middle of it. Or even better, take the iron core and wrap the loops around that, and then you're formed an electromagnet. After just a few, quite a few loops, and a decent current, you're going to exceed any permanent magnet you could ever make. These electromagnets can be made much, much stronger than a permanent magnet ever can be made. Okay. Now, let's look at these permanent magnets. Okay. As I said, all ferromagnetic materials, which are what three elements? Iron, nickel, and cobalt. They're what they call domains are arranged like this. These could be individual atoms, more than likely groups of atoms. And you see, because in a randomly cooled iron, nickel, or cobalt, you would have random orientation because they don't naturally line up like this. Why? Remember entropy, the second law of thermodynamics? everything tends toward randomness, remember? Including magnetic fields. So most of the time, unless they're lined up with the Earth's magnetic field, they come out random. And if they're random, there is no magnetization of them. Okay? However, if you do something to disturb these, or just put them in the presence of a magnetic field, and now these domains start generally lining up with the field and going in the same direction as the field. Okay? And now you've got something that acts like a magnet. Take it out of that, and they probably go back to the original random arrangements, because this is force them this way. But if you perturb them in a strong or any kind of magnetic field, just like that lava, and it was perturbed by the eruption, but they line up with the Earth's magnetic field, then they become permanent magnets themselves. Now this happened to me, and I wasn't planning it. If I had planned it, it never would have happened, but I was, remember my story of digging out the backyard, right? A few weeks before I started that project, when we bought our house and moved in, we noticed the property line, because it had to be surveyed beforehand, the property lines, the stakes they put down, were over from where we thought they would be. A little bit, maybe 4 feet into the neighbor's yard. What's going on here? Well, what we found out was this. When they built the house, I don't know, say 1930s, it was a long time ago, I wasn't even around then, so they put a garage right next to it. And the garage was close to, but not on the property line. So when they wanted to put a privacy fence up, they just went from the back of the garage down to the corner and back like this. Well, the back of the garage was about 4 feet from the property line. And it stayed like that. But, oh, I'm sorry, that wasn't quite true. They put a lean-to shack, okay, a storage shed for lawnmowers, I guess, and things like that. Here's Ethan. Right behind the garage, and then they picked up from there and put the privacy fence. So they put that shed, storage shed, aligned with the outside wall of the garage, and went on back, and then they put the privacy fence from there. Well, by the time we bought the house and stuff, I don't know how old that old lean-to shed was. It was not leaning very well. Okay. It was leaky. It was uneven. Boards tended to look like they were about to fall through. The wood was rotting. We weren't going to use it very long. So, the first part of our backyard renovation was to take down that shed. We had bought another shed at Home Depot or someplace, and I set that up. But we also, when I was doing that, we were going to have to replace that section of the privacy fence, because it was pretty bad shape, about as bad shape as the shed was. So we weren't going to salvage that, and it wasn't all that long. But I asked the neighbor, I said, when they did the thing, is that really where the property line is? And she said, well, I'll have to ask the landlord. She was renting. So she called Tuscaloosa, where the landlord lived, and talked with her, and said, no, the lady said, yeah, the fence is not on the property line. The property line's over in our yard, but that's how we lived with it for years. I said, well, is there any objection to me moving the fence to the property line? None whatsoever. Okay. So I had lined up where the property line was and figured out how many panels of the wood I would need in there, and started digging my post holes. Remember, it was a hot, dry summer, and that clay, rocky clay, it was miserable. I could get a few things of a post hole digger down, and then I'd pour water in it and let it sit. Go to the next one. It was a long process. But I finally got all the post holes dug, got them aligned, put the post in, planted them pretty well. Well, actually, I did the one at this corner and the one up at this corner, okay? And then I ran a string, a tight string, from that corner to this corner. I had a nail up here, nailed it in, and then I did one down here, or I was nailing it. And it just happens that our house sits facing north-south. Front of the house is south, this is north, and I was at the post, and the yard falls off pretty steeply. So this line to be level, you know, up here, I had to be nailing way up here, because it was down. So I needed to get the post in line. Well, I was there. I'm not a very good hammerer, okay? Confession time. My dad used to always say it's because hammers were made for right-handed people, and that, I don't think that was what he said. Anyway, so I was hammering away, and it was a tough old post, and I hadn't planted it too well, so it was moving a little bit, and almost thought I had it in, and bing, it flew out. This is summertime. Grass was pretty thick and stuff like this. I thought I sort of saw where it landed, so I leaned down. I just happened to have the hammer in my hand, and I leaned down and was looking for the nail, and suddenly the nail attached itself to the hammer head. I said, what? Didn't know this hammer was magnetized. It wasn't. I was hammering, facing basically almost due north. And all that perturbing, shaking up those field lines in that, those domains in that nail, it lined the field lines up with the Earth's magnetic field. The nail had become a magnet and attracted itself to the hammerhead. Okay? It was a surprise to me, but I realized, oh, I'm facing due north. Oh, this makes sense. Okay? I never would have guessed it. Okay? I've tried it since then. I've never gotten it to work again, but it worked that time. Okay? So, if you perturb a magnetic material in the presence of a magnetic field, the Earth's magnetic field really isn't all that strong, but it is there. And if you do perturb it in the presence of a magnetic field, over time, I mean, the more you perturb it, you know, bang on it, you know, that kind of stuff, the more you align those domains. And you can make that into a permanent magnet. Okay. So every atom has this, what they call electromagnetic moment. Okay, a magnetic moment. The electron, proton, intrinsic moments are there, and the electron orbital moments. That's what they were talking about in the previous slide. This is the intrinsic spins of the electrons and protons, and then the orbital motion. Somehow all those things together will produce, in these three metals, a magnetic moment. Okay? That doesn't mean a moment in time, that means a writing moment. Okay? These clusters of the atomic moments align in the domains randomly at first when they're not magnetic, but then when you perturb them in the presence of a magnetic field, the stronger the field, the better, then the domains do align, and you can make yourself a permanent magnet, like I did with the nail. Okay? Unknowingly, but did it. Okay? Now, let's look at Earth's magnetic fields. These originate, as we said, deep beneath the surface of the Earth from currents in the molten core. The outer core is molten, meaning melted. Around that is the mantle, which is not smooth and even, or even if it is, it's spinning, and the liquid molten core is not spinning as fast. So there's friction, and the magnetic moment that we have there then creates a north pole, and this is what's bizarre. We named it wrong, okay? If that really was the North Pole, then south poles of magnets would point to it, wouldn't they? But because we say the North poles of magnets point to it, that means that has to be a south pole, okay? So that seems a little bizarre, but it doesn't matter. It all works, okay? Now, our magnetic North Pole and South Pole do not align themselves perfectly with the geographic north and south poles. Actually, why, I don't know. Distribution of iron, the way the magnetic fields go, I don't know. I do not know why. Here's our good old handy-dandy visual aid. This is the Earth. Of course, the actual spin axis is the North Pole and the South Pole. That's the true North, true South. Okay? The magnetic North Pole is close, really close, but not quite there. It always takes me a while to find it. The North magnetic pole is right about there, pointing right towards that. Okay, he drug him in here. Okay, that's within. Make sure this is. No, I'm looking at a little more. Where's one? 45, 60, 75. It looks like it's between 80 and 85 degrees north. There's the North Pole is 90. So it's really, really close. Okay, let me mark J here before I forget he came in. Okay. All right. So right now we're only missing Latricia and Mendez. Okay. Good attendance, folks. This is a really good attending class. For some reason, the South magnetic pole is a little further off. Okay? And it takes me a while to find that too. Here it is down here. It's actually outside the Antarctic Circle. It's that far off. Okay? It's between 60 and 75. It looks like about 65 or so degrees south. Up here it's around 85. 65 degrees south, where the South Pole is 90 degrees south. So it is pretty far off. Now, there's another ramification of this. These poles are where the field lines of the Earth are the strongest. Remember, if you sprinkle iron filings over a magnet, they all congregate at the poles. So that's where they'd be the strongest. So the field lines of the Earth are strongest there. And cosmic rays and other things that come through our atmosphere from the sun, they align themselves, or when they get in the presence of our strong magnetic field there, they do some strange things. One of those strange things is produce a beautiful light show. Does anyone know what those light shows are called? Northern Lights, exactly. Okay? There's another more technical name for it. Aurora Borealis. Bora means cold. Aurora means light or rain, basically. So it's a beautiful display of cold light, okay, because it's up there near the poles. That's the Northern Lights. They also have them down south. And remember where I said the South Magnetic Pole was? Really close to what country? So those lights are called Aurora Australis. You know, hard to say after Australia, because that's where you see them the best. Because you're close to it when you're way down south in Australia. Now, I was down in Tasmania, but I didn't have enough sense to go out at night and see if I could see anything. I think they're a little further south than Australia is, but Australia is the closest land. So, anyway, because the poles don't line up, that means that compass, that magnetic compass, is pointing to the North Magnetic Pole. It's not pointing to the true north. So there is a little offset. And you call that your magnetic declination. And depending on where you are, that could be pretty significant or maybe not very much at all. The direction of the field periodically reverses. Now that is strange. Now when they say periodically, this is one long period. About every million years, 1.5 million years or so, it will make a change. Now, I don't think it's instantaneous. Of course, we haven't been around 1 million years, so we have no record ever changing, but we can tell that our magnetic field is weakening some now. And that kind of makes sense. Okay, at least to me, okay? If there is some sort of weird thing happening there, my guess, and by the way, how do they know this? By layers of that magnetite, iron ore, lodestone, that is lined with the magnetic field. They can go down, drill cores, and they'll find some that point this way, and then several layers down, they'll find some pointing the other way. In between, they find iron that's not magnetized or very weakly magnetized. So in my mind, this is sick little mind of mine, it probably follows a sinusoidal curve, harmonic type stuff. Up here, it's the strongest, and then I think we're on the downhill side of the string. At some point, we may not be around then. We won't, but mankind may not. It will almost be no magnetic field. So those guys out there with magnetic compasses won't know where to go, okay? And then you'll start seeing a weaker field and then a strong field, but the needles point in the opposite direction, so you just change the names. You should say that's north and that's south, make a new compass, okay? But the direction of the field, they know it because they drilled down and found layer after layer after layer that reverse. I think about 22 times that they found layer reversals. The last reversal they think was about, judging by the depth of the rock and the fossils and things they found around it, and doing carbon dating and stuff like that, about 780,000 years ago was the last time they found rock. Rock that old was the last time it was pointing in the other direction. So the odds are we're not going to see a change. Not likely. Okay. Here is the illustration of what we're saying here. If indeed you put a magnet in the middle of the earth, this would be a south pole up here. Why? Because all of our compasses point toward it. Our north points toward it. That's why we really should call our north poles north-seeking poles. And the book has called them that a little bit, meaning they seek the north. But it's not quite aligned with the true north. Just a little bit off. And of course this would be the south because, so the field lines, remember, always go from north to south. So that convention has it that because your compass is aligned with these field lines, that would have to be a south pole. But it doesn't matter what you go. They're binary. You can name them one way or another and then flip them if you want to. When they flip, you flip. Okay? Now, here are the declinations for the U.S. Okay? Now, just as a matter of looking at it, here is always hard to find. The magnetic North Pole, there's true North Pole. If you tried to go down pretty much here, they don't follow this exactly, but pretty close. It goes almost straight through the U.S. Actually, it varies a little bit because it's off down here too. So it doesn't follow these lines exactly. It follows a line more like this and cuts through to head toward the South Pole. That's South America. So here are the declinations. Now, it's probably hard to see from where you are, but if you got your book, right up here, the upper peninsula of Michigan, through much of Michigan, down in the northeast corner of Indiana, down to where Indiana, Ohio, and Kentucky meet, smack through the fat part of Kentucky, down through that Chattanooga is real close to this, Knoxville over here, Tennessee, then North Georgia. Boy, Atlanta's not far off from this, not far at all. And on down, cutting Georgia almost into the northeastern part of Florida. This is a little bit east of Tallahassee, but not too far. And then exiting somewhere here north of Miami, that's the zero line. There, your magnetic compasses are going to point straight toward true north. Since we're over here in Birmingham Bessemer area, we're about, I can't read that number from here. Can y'all from your book? Where is it? Don't tell me they left it off of this book. Oh, I think it was back of, yeah, it's back a page. We're somewhere around 2 degrees off. Not much at all. So this is the 2 degree. Now, they say east, you say, but we're west of this. Well, that's because the point is 2 degrees east of where it should be. I mean, it's pointing that way. So 4 degrees here, 6, 8, 10, 12, I think that's 14, 16, 18, 20, and 22. Is that right? Yeah. East. Where it's going up this way, is that 2? No, much wider up here. It's 6. Strange. 6, 10, and 18. 6 degrees west, 10 degrees west, and 18 west. So over here around Seattle, your compass is not, magnetic compass is not the best. Okay? Pointing generally north, but it's off. It's pointing east of what it should be. True north, you have to go west of that. Over here, it's pointing west of where it should be. 18 degrees. So in Portland, Maine, or around in those areas, yeah, you're off a bit. We're pretty lucky. 2 degrees ain't bad compared to everybody else. Okay. Any questions on that? Okay. That done, we're moving into 6.4. Electric currents and magnetism. Now, I've been saying this, so here it goes again. A moving charge, which is a current, moving charges produce magnetic fields. That's the only thing that produces magnetic fields. So guess what, folks? Charge, which is electricity, and field, magnetic fields, magnetism, they're hand in glove. You're talking about the same thing. You don't have magnetic fields without moving charges, and moving charges always produce magnetic fields. Okay. Here's the example I was giving before. If you have a wire here, now they show electron current. So if you're doing electron current, you have to use your left hand. So put your thumb in the direction of the electron current, your left fingers will point in the direction of the field. Or better, get you a little compass that may be pointing true north here, but put it here, it'll be pointing that way, here this way, okay? Because your compass aligns itself with the magnetic field produced by the moving charge. What kind of current is this? DC, direct current. Because if it's AC, compass doesn't know where to go because it's changing so rapidly, it just points north. You know, it doesn't even bother. Okay. Now, let me see. I did want to point out if we're, no, I don't think we've missed any major figures here. All right. Now, the shape of the field is determined by the geometry of the current. So certainly a straight wire is going to produce concentric circle fields. Okay? That's what we would have there. However, as I said before, make a loop of that wire, and now your fields, I'm going to use right hand, if the current is like this, the field, your fingers are pointing north, they're going up. So this is your north pole, that's your south. Okay? One loop is going to reinforce those wires, those fields really strongly. Especially if you make it a nice tight loop, you know, a small diameter of that. Okay? Now, continue making more loops, and what you build is a solenoid. Any of you use solenoids for anything? Yeah. Okay? And basically, they are little magnets. Okay? That's exactly what they are. Electromagnets, so to speak. So here's the thing I was saying about a single loop. Now again, they're showing electron flow, so you have to use your left hand. If the electron flows like this, the magnetic fields are going around the wire in that direction. So if they continue going around the wire in that direction, all the way around, then in the middle of the wire, they're pointing up, so that's the north pole. South pole would be this way, okay? And notice how they reinforce each other big time. The tighter the loop, the more they reinforce, okay? And then make several loops. Well, no, they're still showing this. That last figure then had the magnetic field going like this, because all the, that was left-hand rule, like this, they're all, I'm going to pull my shoulder out of the way if I don't want you. Your fingers are pointing upwards, so that's your north pole, south pole down here. Because the field lines always point away from the north toward the south. Okay, so that's your field. A single loop, okay, a single wire, very weak magnetic field. One loop, you strengthen that field many times over. Then make a bunch of coils. Make sure you go in the same direction, okay? And again, they're showing electron current. Why they're doing this, I'm not sure, but they are. So left-hand rule here. So now the field lines are began pointing north, so there, that's the way they're pointing here. Then you go round and round and round and round and round. Make sure you don't reverse your direction. If you do, you destroy your effective magnetic field. But keep going in the same direction, same direction, same direction. Nice, tight circle. You, lots of lines there. You get a very strong magnetic field with a fairly small current, okay? Stronger the current, the stronger the magnetic field. Have any of you ever seen any of these at work?
Relay.
Yeah, relays, of course. We'll talk about some of those later. Bobby, an electromagnet. Say again?
Motors use electromagnetism.
What did you say?
Motors, like electric motors.
Oh, absolutely. You're big time. You're absolutely right. We're going to talk about those. But have you ever been to a junkyard when they were loading stuff? That thing that picks up cars at a time. They set it down here, turn on the juice, magnetize, pick it up. That's a strong magnet. Pick up the whole car, put it here, turn off the juice, tops it down. That's what electromagnets do. We haven't quite gotten that far, but I just couldn't resist it. I could have, but I didn't. So here's what electromagnets are. You take that coil of wire and stick a ferromagnetic core in it. Now the most common of those is iron, okay? Nickel and cobalt are not nearly so common. Cobalt especially not common, but iron all over the place, okay? Put a ferromagnetic core, and now you've got an electromagnet. The current-carrying wire wrapped around the core produces the field, the core enhances it, okay? Now you've got an electromagnet. The field is enhanced by the combination of the wires and the core, okay? It can be turned on and off. And you can make these really, really strong enough to pick up cars. Bundles of cars, crushed together cars. Pick them up, float them on. Go down to Mobile, where they pick those up, put them on the ships. The trailers off big old trucks. Pick them up, move them on. In the old days, they had to wrap cord lines around those, get them all balanced well and stuff, and they still had accidents. Got electromagnet, put it on, turn on the juice, move it over, set it down, turn off the juice, go back. Much faster, much safer. They're used in many applications. Y'all were just saying. All of your meters, remember the ammeter we use electromagnets. Switches, you were talking about relays, speakers, all the time, your phone, okay. Motors, generators, they all use electromagnets. We'll look at a few examples here. This could be, this electric meter, and right now I'm going to name this a voltmeter. No, they're going to do an ammeter, okay? The instrument for measuring current, ammeter, the one we use in lab, right? So what do we do here? We connect it to a voltage source. So you got DC current flowing through the coil that's wrapped around a core here. Okay? You have a spring to offer resistance. And when there's no current, it zeroes out over here. Now that's a needle. It looks like a pencil point, but it's a needle. Okay? It zeroes out. You put current through here, and now I forgot to mention. Look at the casing here. A big, strong, permanent magnet. North pole here, south pole here. We call it a U magnet, horseshoe magnet. Okay? The field lines here are going this way, from north to south, north to south. Bunches of them, tight. This is a strong magnet. You put current through it, and now if this current makes this, the North Pole is going to be repelled and move this way. Of course, the South Pole will be over here. It gets repelled and move this way. And the spring gives it the tension. All you have to do is calibrate your meter, and you can read what current is producing that much of a tension. Okay? That's a very simplified ammeter. Okay? All you do is change the units, and you've got a voltmeter. Okay? Because you increase the voltage, same resistance, you're increasing. You can now measure what voltage you got going through there, and that's what the generator, the box we were using, that's how it measures its voltage. Okay, that we're reading off of that. It uses the magnetic field produced by the current to react with the magnetic field between the permanent magnet here, and you get a deflection. The stronger the field of the current, the stronger the current, the stronger the field, the more the deflection. It's proportional to the current. The proportionality constant basically is your calibration. And you know how to do it. Now, modify it very slightly, and you can measure potential, which is a voltmeter. Because if you're not measuring current, you're measuring voltage, because same thing, increase voltage, you're going to increase the current, and that increases the field. Okay. Now, you have to do the inverse, and our little knob there would do all that for us. You didn't know what's going on inside, but it reverses things, and now it becomes an ohm meter. Why? Because the resistance is inversely proportional to the current, inversely proportional to the voltage. Okay, so you have to, inside the electronics it changes. In the old meters, you would measure current going this way, voltage moving this way, and your scale would read resistance coming this way. You'd have to just read the scale backwards. Different scale, of course, and you'd use the same needle, but you just measure it coming this way. So it's pretty clever. Electric meters use electromagnets, every one of them. No way around it. Okay? Someone mentioned relays. I think it was Lugan. Certainly those are electromagnetic switches. Okay? They use a very low voltage to control currents going into the relay. Okay? Here's your small current relay circuit that keeps a certain field there that's steady, it's constant. Okay? Now, what happens here, let's just imagine this is your thermostat. Okay? They've taken the cover off that, and I don't know why. Nothing that you can see under there, but it just doesn't look good to have that uncovered. And remember, we have these bimetallic coil that expand and move. Here's your vial of mercury in a glass vial here. And as it heats up, and it goes one way or another, it'll probably heat up going this way. And when you do that, this electromagnet, sort of hard to see here because this is done. this is connected with a switch. It sends a current or doesn't send a current, okay, depending on where it's located. And what happens here, the electromagnet, as the current gets stronger, it pulls this against the spring here, pulls it, makes contact, and your heat pump comes on. So say the temperature got cool, and that was enough to make this stronger, pull on that, the heat pump comes on. Doing a little bit of adjusting, you could get it so it went the other way. It could turn on the AC. So this is how, in a really raw, rough illustration, how these switches work. Small current here controls a big current here that runs your heat pump. So the small current relay switch, almost negligible amount of power it's using, but it controls something that uses a whole lot of power. So it's much more efficient that way. All right. Now, when they say telephones here, they don't mean your cell phones. They mean, have any of you ever seen those that you actually held up to your ear that had a speaking thing? Oh, yeah, you've seen those. Good. Okay. In a few years, that won't happen. Let me give you a dumb story. It has nothing to do with what we're talking about. My niece, actually my wife's niece from Huntsville, her dad's a dentist. So they and his sister's husband ran a car dealership up in Memphis. And so anytime they wanted a new vehicle, they got really good deals because their brother-in-law gave it to them on really good terms. So they always had pretty good cars. I had an old pickup truck, okay? And Michelle went with me somewhere in the pickup truck, and when she came home, she just was, I didn't know this, she went running in the house and said, "Mom, Dad, Uncle Charles has the coolest truck." She said, "There's this thing on the door that when you turn it, the windows go up and down." She had never in her life been in something that didn't have electric windows. When you turn this knob, the windows go up and down. That was so cool. Well, those people, what is that you got in your hand? Well, the old phones, that's what we're talking about here. Let's get the old guy talking into the phone. He's the only one that uses them anymore, right? All right. Now, he's speaking into the phone. Now, when you speak, if you hold your hand in front of your mouth when you're talking, you'll feel a little burst of air. That's what's carrying the sound, is compaction and rarefaction of air waves, air particles. That's what makes you hear. Your ear has a very sensitive eardrum and other things in there that magnify and stuff, and that's why you hear, because they're picking up this tiny little vibrations, incredibly small vibrations. We're amazing machines when you think about it, okay? Absolutely amazing. So these air condensations and rarefactions go through the holes in that speaker, and look at what you got here. We have a metal diaphragm, and just behind it are carbon granules. Now, carbon's a good conductor, but the granules are very small, and when the compressions hit it, they press these closer together. That makes for better current, more current, because there's better connection there. And that greater current then, they don't show it, but it's connected with the electromagnet, and that electromagnet, well, it sends a pulse of electricity because current, let's just leave it like that. Sends that, okay? Now, let's see if they show the receiver. On the receiving end, then these varying currents that come through here's a permanent magnet here, and then there's an electromagnet here, okay? It's shown expanded here, but it's electromagnet. When the current hits here, then it attracts the permanent magnet, which pulls the paper cone in this way, and then when it hits a weaker current, it comes back out, produces compressions and rarefactions, condensations and rarefactions. What's happening then? You hear through the receiver the same voice, I mean the same sound that went in to make it. And how in the world it can get not just sound, but sound that you can distinguish. Like a lot of times people that you're used to, you can pick it up and say hello and say, oh, this is Judge, or whoever, because you can almost recognize the tone and tenor and rhythm of his voice, right? Now, my father-in-law happens to speak at a frequency where my hearing loss is the worst. I can never recognize him. I can hear someone talking and I can't make out anything. His frequency is just at my band frequency in my ear. I feel really bad because I never recognize him. If it's someone I don't recognize, it sounds like he knows me. I say, Mr. Brazil, yeah, okay, yeah. I act like I can understand. Okay, there we go. So the speaker, the varying current that you got from here changes the electromagnet, moving the permanent magnet, and that moving permanent magnet vibrates the comb and then sends out condensations, compressions, rarefactions. And that's the sound you hear. And I wish they had put this over like this, because this part's up here and this part's down here. Never mind. Obviously, the graphics guy knew what he was doing, or gal, or whoever. Okay. Now, before we move too much further, there is an interesting little blurb that's called Concepts Applied. And you can actually do this if you want to, and you'll find it pretty interesting, probably. But let me back up and give you the first time this happened. What they talk about is making a lemon battery. They say take the lemon and roll it in your hands really well so you're breaking some of the thing and getting it real juicy inside. Then stick a copper wire in one part of the lemon and a paper clip in the other. Paper clip's made out of metal, iron, something, whatever. Okay, different from copper. That's the key. And then you can wrap that wire around the compass and deflect the compass. Why? You've just made a battery. Okay? Two dissimilar metals in a conducting fluid. Lemon juice is a really good conducting fluid, and the two different metals create what they call a potential difference, a voltage. And that voltage creates a current, and you can deflect the compass needle with that current. Okay. They wrap it several times so that it's stronger. The magnetic field is stronger. Now, the first guy who did it wasn't a lemon. He was actually an anatomist. Did I tell you the story already? Okay. He was an Italian anatomist named Galvani. Anyone ever heard of galvanic cell or galvanic block or galvanic anything? Y'all too young. Okay. Anyway, he was studying the tissues of a dead frog. Okay? He was trying to isolate what were the arteries, what were the veins, maybe the nerves, and looking at the muscle tissue, just studying. It was a dead frog. Okay? And not only had it been a dead frog, it had been stored in formaldehyde, which is that really smelly stuff, but it keeps it from rotting. So I'd rather have that smell than rotten frog smell. So anyway, it was stored in there for a long time. And then he had cut the leg off. Okay, so a dead frog, cut a leg off, and he was trying to study the various tissues in that frog muscle. Okay, so he had him a little set of tweezers. And I'm just going to make a guess they were iron tweezers, okay, or steel, something like that. But he also had a little probe. Now let's just say it was copper, whatever it was. It wasn't iron. And what he did, he was holding the frog leg with this and went to probe it with this, see if he could separate the tissue. And the minute he touched the probe to the frog leg that he was holding with the tweezers, it jerked. And when he cleaned his pants, when he realized what had happened, he said, wait, this is a dead frog leg. How could it move? I've just discovered the nature of life. I don't know how or anything else, but I've just created life. Whoa, Well, he tried other things and found out, it's only electricity. Of course, they didn't know much about electricity back then. But another Italian scientist named Alessandro Volta Have I told you about Volta before? Yeah. Yeah. Lake Como, Italy. He heard about Galvani's work. Galvani wasn't interested in the physics of it. He said, let me into this stuff. And he took those metals that he was using and created one in his lab. Sure enough, he produced electric voltage, electric current out of two dissimilar metals and a conducting fluid in between. And he started making what he called his PILES, P-I-L-E-S, which nowadays we call batteries. And he did a lot of work on this, and that's why we named the Volt after him. So the first person who did something like this and recorded it was Galvani. Now, with a bunch of guys in the classroom, I'm afraid I'm going to know the answer to this before I ask you. Have you ever had a battery in your mouth? Yeah, I knew they were going to say yeah. Not an actual bulk in the store battery. Okay? Have you ever made a battery kind of in your mouth? I bet you have. If you've had any dental work done, do any of you have fillings? I do. No. Wow. You have fillings. Are they sort of silvery looking? Gold? Second?
Clear.
Clear?
Or white.
Okay. Now yours may not work yet. Yours are ceramic, I bet. Okay. The old days, they had what they call silver composite fillings. Okay, silver's a metal. And I don't know if lots of places you could have it. Aluminum foil, used to wrap chewing gum in, or just aluminum foil that you use to grill something, but happen to get a piece of foil and you bit down on it. Does that ever happen to anybody that had a filling in your mouth? Huh?
When I was a kid.
Yeah. Did you notice something?
Yeah.
What?
Like it felt like it was kind of like a shock.
Yes, you're exactly right. You just had a battery in your mouth. You had two different metals, silver and aluminum, with a conducting fluid, saliva, and you had a little battery. And you bit down on that, and there went a current. And guess where that filling is close to? Your nerve in your tooth. That's what the shock was. It was that. So if you have any, do it. It doesn't hurt. You'll just be surprised. Bite down on a piece of aluminum foil. You'll get right off of it. It's a nice little jolt, but it doesn't hurt that much at all. Okay. So that was concept supplied. Then we had the figure that we had the previous one. And let's move on to electric motors. Oh, okay, that's at the bottom of page 161. What an electric motor is, it converts electrical energy, you plug it into the wall, and it starts spinning. I mean, when you connect the switch, into mechanical energy. That's what a motor does. That's what starts your car, right? You turn the switch, and you connect the starter motor, and it starts the whole process. Once it's going, you don't need that starter motor anymore. It keeps itself going, okay? But that's a motor. Your weed eater, whatever. You have electric lawnmower, that's going, okay. There are two working parts to every electric motor. One is a field magnet. Does that look familiar? Okay? Just like in your meters, you have a strong magnetic field. It's set up this way, north over here, south, doesn't matter which side, so the field lines go from north to south. Okay? Now, what you have here is then an armature, which is a movable electromagnet. Okay, these are windings on the core here, ferromagnetic core. Okay? And you have a commutator. Anyone know what a commutator does? Okay, what does it mean to commute? Okay, but then usually you go back again, right? I commuted into work this morning, I'll commute back home. Right? Say again? That's it, exactly. It's going one way and then the other way, one way and the other way. every time around, it switches the polarity. So when you start this thing, connect the switch, okay? Then the north repels this north, the south repels that south. The armature can spin, and just about the time it gets halfway, because guess what? It's going to, about the time it gets all the way over here where the north is lined up with south, south lined up with north, it would tend to stay right there with it. It would be happy camper right there. But right when it does that, then it switches the polarity, because the armature then changes direction, and now this one becomes the north, this one becomes the south, and it starts the process, and it goes. And it spins like that. That's what an electric motor does. A very efficient machine, because it's only dealing pretty much with field lines, okay? Currents, there's probably some heat produced and stuff like this, but generally a very, very efficient machine. No friction here, to speak of, except in the wires, pretty much. The armature rotates by interactions with the field magnet. The commutator and the brushes reverse the current to maintain the rotation. Right about the time it gets where it thinks it's going to stop, it doesn't. And it reverses and it keeps spinning. Spins. Usually there's a flywheel or something like that on here to even out any jerks and fits and starts that you would have. All right, now we're moving here into, now I want you to remember that motor and how it looked and how it was put together. We're moving now into 6.5 electromagnetic induction. Okay, remember what produces a magnetic field? Second, a moving charge, current. That produces electric field. Okay? Now, electromagnetic induction sort of goes the other way. Relative motion between a magnetic field and a conductor is going to produce electricity. Okay, moving charges produce a magnetic field. Changing magnetic fields produce electric current. One does one way, one does the other way. The changing magnetic fields near a conductor will create a current. No battery, no nothing, except the moving magnetic field. Okay, changing magnetic field. So here's what we got. You got a bar magnet here and a coil of wire. No battery, nothing. This is sitting at zero. No current flowing through here. Why could it be? It's just a wire going from one pole to another pole. You drop the magnet through the coil when this changing magnetic field, it was zero basically, then it got very strong, and then it started weakening again. That's a changing magnetic field. When that north went through, you got positive current. Now, they didn't show this, but then when the south fell through, it goes negative, because now it's the opposite field. Now you not flip them around, you move the south going up like this, changing the field lines here, the changing field inside the coil, and when the north goes through, back positive again. Happens every time. Every time that magnet would fall through. One time for north, one time for south. The effect is what we call an induced voltage and current. That's what we call it electromagnetic, because the changing magnetic field is producing an electric current. It's inducing an electric current. So it's electromagnetic induction. Okay? So induced voltage depends on the number of loops. Sound familiar? Like your electromagnet, number of loops, the stronger the magnet. So the number of loops, that would be the voltage depends on that. The strength of the magnetic field, if that's a really strong magnet, then it's going to be more. Fairly weak magnet, a little bit less. And the rate of the magnetic field change. So if you could figure a way to change the rate that that's changing. Now, here's what we'll be doing in lab. Okay? We will have, and by the way, here's another key to this. All it takes is a changing magnetic field, relative motion between the magnetic field and conductor. So you could either have the magnet spinning inside a coil, or you could have the coil spinning inside a magnetic field. Either one will produce a relative change in motion between the magnetic field and the conductor. And that will determine how strong, these factors determine how strong the electric field is. Now we turn around to generators. Now there is a concept applied on how to make a simple generator, and if it's the one I'm thinking of, no, this is a different one, but you can do this. The one in the book is fine. Before we get on to generators, at the top of page 163, it says the current war. You might say, oh, what war's going on now? That's not the current it's talking about. What they're talking about is the war between different types of currents. Okay? Now, what two types of currents have we talked about? AC and DC. Who was the father of modern electricity in the U.S.? The greatest inventor of electrical stuff. Light bulbs, phonographs. Thomas Edison. Brilliant. More of an engineer, I think, than a scientist, but definitely a really, really strong scientist, too. He obviously was a pretty rough old cuss, too. I think not the easiest person to work around, because he was a workaholic, and he also was focused. He was deaf. There had been an accident in his childhood. I think someone had slapped him in the ear and lost the hearing in that one ear. He actually said it helped him be more focused because he cut out all the noise around him. But anyway, I think he was a tough old cuss to work with. But he was convinced alternating current was dangerous. It would kill you. You know, you don't want to mess with it. Direct current, he thought, was much safer. Okay? So he thought that was the future. I mean, he was at the beginning of the future of electricity, widespread common use of electricity. He had a guy working for him for a while who was another brilliant engineer, very brilliant scientist as well. He was an immigrant, as a lot of people are, and he happened to come from, I've heard both Serbia and Croatia. At the time I was hearing all this, all that was called Yugoslavia. Then Yugoslavia split up and became, again, Serbia, Croatia, Bosnia, Herzegovina, or whatever, you know, all these other smaller countries. He was one of the two from one of those two countries. He may have been Serbian from Croatia or Croatian from Serbia, I don't know. But anyway, he came over to the U.S. Brilliant character. Went to work for Edison. And in many ways, they were synergistic. And they did greater things because they were working together. But in other ways, they were antagonistic. And after a while, they had to split. They were just two strong of personalities, strong of intellects, and they were neither one very good compromisers. There was another guy whose name is known better than probably most of them. All of you know this name, Westinghouse. You've heard that, haven't you? You haven't. Appliances. Westinghouse washers, dryers, refrigerators. It was a brand name. But anyway, I think his name was George Westinghouse. He thought, but he was a businessman, he just had a gut feeling that alternating current was the way to go. Well, Tesla, did I say his name? The Croatian that worked for Edison, his name was Tesla. Nikolai Tesla. Now they named the car company after him. What kind of car was that? Electric car. Okay, that's why they named that. Okay. So, Tesla was convinced alternating current was the way to go. He actually had a few accidental discoveries, but he was smart enough to figure out, hey, this is important. And I think he was really big on discovering induction, okay, and how to use induction, okay. But anyway, when he found that Westinghouse would support him, he started working for Westinghouse, and unfortunately, guess who won? Westinghouse and Tesla. Alternating current is how we power the U.S. Direct current still has uses. All your computers, all your cars, all your cell phones, lots of things depend on that, but that's all short range. You can't move DC current very far. You have a lot of line loss. Alternating current, different story. So, that's just because that was top of the page there. That's who it's talking about in the current war. Hey, guess what? These are potential paper topics, folks, right? You know what's coming up? The end of the term. And guess what's due at the end of the term? Preferably before the end of the term? Your research papers. I've gotten a big 4 in already out of the 13 students in the class. That's less than a third, by the way. Less than a third of you have turned in the paper. Please use this Thanksgiving break to get those knocked out. I don't want to be taking off points for late papers or giving zeros for no papers. Okay. So let's move on to generator. The structure, does this sound familiar? An axle, which you could almost call what did we call it before? Play this fun. Goodness gracious, the old gray cells. Armature. The axle or armature of wire loop, and the axle turned mechanically to produce electrical energy. And actually, if I'm not mistaken, they were actually invented reverse order. They did generators first. And then someone at a World's Fair, it seems like it may have been St. Louis or somewhere, was setting up to demonstrate a generator, and he got his wires crossed, and he made an electric motor. He went, whoa, and then he realized, hey, this could be useful. And so generators actually came first. So what you have is an axle with main wire loops in a magnetic field. Hey, that sounds just like your armature in a strong magnetic field. The axle is turned mechanically. Now before, your motor, the electricity turned the thing so you could cut your grass or drill or whatever you want to do. Yeah, you drill whatever you're going to do, okay? Now we're using mechanical energy, moving water, steam turbine through, whatever, to mechanically turn so you produce electrical energy. That's what a generator is. Now, an AC generator, of course, produces alternating current. That's what AC stands for. And that's what all generators really are trying to produce, okay? What you do, you just hook it up, and the sign of the current and the voltage alternate. I wish they didn't say it that way. When the current is positive, the voltage is positive, the current is negative, the voltage is negative. But they alternate, both of them alternate as it turns around. That's why it's AC. Okay? Now, to make it a DC generator, that's sort of like a battery, but it's not. Okay? That's really what our devices are in there. You have direct current. What you have to do is swap the sign of the current and voltage every turn. So what might do that for you? What did it for you in the motor? To and from school? Commutator. Yeah. Put the, let's see. How is it? Old Dewey White used to say it. I can't remember. Emphasis on the wrong syllable. Okay. So anyway, just change your. Nope. Okay. So here is your what is producing electricity. You have a strong permanent magnet. They keep flipping the thing. The field lines here go from north to south. They're almost straight, almost uniform. Strong permanent magnet. Now, you also, it doesn't have to be a permanent magnet. It can be electromagnet. You just put your field coils here, around here, and that produces a strong, very strong electromagnet. It's just that you're measuring, but the field lines are like this. Okay? Now, your axle is out here being turned by something. You can turn it by hand like we're going to do in the lab. You can turn it by water like you do in a hydroelectric plant. You can do it by steam like they do in a coal fire, natural gas fire, or a nuclear power plant. However you're going to do that, you're going to turn this in that strong field. Now, these are current loops. These are loops. Okay? Now, what is happening, you're turning this for some way, and here you're cutting maximum number of field lines. That coil is cutting the maximum number. And as it turns, by the power, your whatever, as it turns, now the field lines are being reduced. Here you have no field lines. But then you start increasing the field lines again. Here they're decreasing, here there's zero, there they're increasing but in the opposite direction, and then they decrease again, go to zero, and then increase in the opposite direction again. So what they do for AC, you put one of these, and this is sort of crude, but you have one, and you have terminals going in, and the current just oscillates because every time it turns, it changes direction of the field. So your mechanical turning of this is producing electricity that you put out here. Okay? Now, here's what it looks like. For a while there, it's positive, maximizes, goes to zero, becomes negative, minimizes, then goes back up, goes to zero, positive, negative, just like I showed with the, over a long period of time, the Earth magnetic field, in my opinion, but that's just my opinion. So that's what happens with an AC generator. Now, what makes a DC generator? Everything looks the same, doesn't it? Except down here, you have a split ring commutator. Now, they don't identify it here, but that's what it is. Notice the ring is not solid, it's split. So when this turns so far and goes to change signs, then suddenly, when it does change sign, you change which wire is connected to it. So this stays negative, and this stays positive. This turns, and when this one's negative and that one's positive, things are fine until it, right before it changes, then it switches those, but this stays negative and that stays positive. So you form a DC current, direct meaning it always goes in one direction, but it's not uniform. It's called a pulse DC circuit. You have a max here, it goes to zero, but then right at the time it would go to minimum, it flips the side, just like the commutator did before, and puts it positive again, and positive again, and positive again. So what you have is a pulse DC current. Okay? The sign of the current and voltage stays positive. The current and voltage aren't constant, but the sign is constantly positive in this case. We'll do it in the lab so it's constantly negative too. All right. Let's flip a page here. How are we doing on time? Oh, good. Okay. Now. Oh, here we go. That was generators. One paragraph in your book. Under that is transformers. What does a transformer do? I don't mean it turns into a car into that's movies. Okay. What does a transformer do?
Transforms lower voltage with a high current to a higher voltage.
Excellent, excellent. There are problems that you run into with power transmission. It was the very thing that Edison was worried about and that Tesla and Westinghouse were trying to fix. Okay? But they came up, they didn't, but over time, people figured out sort of a compromise. So, if you're running a safe kind of voltage, that's a fairly low voltage, usually you got a lot of current. Because guess what? Power, which is energy per unit time, that's what power is. Energy is neither created nor destroyed, right? It's conserved. So the energy remains the same. So energy per unit time is the same. Your power is constant. Okay? And if you're running a low voltage, that means you have a high current. Remember what? Remember that? The power equation, I'll put it down here in black. Okay? Power is equal to current times voltage. Remember that one? Okay? Now, if the power is constant, if you go to low voltage, you have a high current. And guess what? High current going through wire, lots of heat. Lots of heat, lots of line loss. You have inefficient system. And the lines get hot. Your insulation bubbles. I mean, it's not a good picture all the way around. Okay, so what they do, just like what Logan said, they increase the voltage when they're going to go long distances, increase the voltage. And they may do it in several steps. And these big old towers you see that set way up in the high, the iron steel towers, and they have the trees cut out from under them. They go across country, taking that electricity for long periods of time. Super high voltages. Very low current, very low line loss. Okay? Then they pull off and go into, oh, here he is. And Daz is here. So now we're only missing Latricia. Okay. She's having to work. She either got a new job or they changed her hours on her, and she has to work while we're in class. She's trying to follow online through the videos. So what they do when they come into town, somewhere outside of town, usually there's some big substation. Okay? Owned by the power company, usually a long way from anybody. Don't want anyone living too close to it. They won't want people messing around in it. They put fences and barbed wire and all sorts of stuff around it. Keep people out, keep them safe. And there they have transformers that cut down the voltage but increase the current. And then they move the electricity through town, still at a fairly high voltage, but much lower than what it was on those big towers. But the current is just a little bit greater. But before it can come into your house, that's way too high a voltage. So somewhere out, wherever you live, go outside and look where the wires come in on the nearest power pole. You'll see something like that, won't you? That's a transformer. And that drops it from whatever the fairly high voltage, but not too high, that was going through town, down to what you can use in your house, which is basically usually around 360, isn't it? And then they split it off, some 240 and some 120, or did it come in at 240?
I know on the telephone line, or at the top of the pole, before it hits register, it's like 7,000 volts, but it's usually 240 coming in.
240 coming in. And then the 240 goes directly to your oven, your range, your anything that uses a lot of heat, your clothes dryer, you know, anything, those big old 3-prong plugs, those are your 240s. But then you can also, then they cut it in half and split pretty much and send everything else to your plug, like wherever they are on the wall here. And that's your 120 or 110, somewhere in that range, 115, something like that. So this takes it down from, you said around 7,000 coming in down to around 240 going into your house. So the amperage there is pretty long, but yeah, it's a pretty short distance. And then all that it does in your house, that's pretty short distance, okay? But to get from the substation to here, probably miles. So they want high voltage, okay? Now, so here's the problem. High current produces high resistive losses. Because high current produces heat, that's wasted energy. High voltages are dangerous, potential differences. You don't want to hang around them too much, okay? You don't want them coming into your house that way. So the solution is a transformer. It either boosts or lowers the current or the voltage, but in different directions, okay? The basic relationship is power in equals power out, okay? And here's the key. And remember, we said this before. If you wanted to increase the voltage, you increase the number of turns, right? So the number of coils corresponds to the voltage. That is a direct relationship. So, if you divide by the number of turns then, voltage on the primary side, whichever this is step up or step down, is related to the number of turns on the primary side, as the voltage on the secondary side is related to the number of turns there. If this is an increase in number of turns, it's a step up voltage. If it's a decrease in number of turns, it's a step down voltage. Okay? The number of turns in the primary and secondary coils. This is the voltages of the primary and secondary coils. This is the relationship that has to be met. Okay? Now, let me get my writing off of there. And here's an example. This is a very simplistic example. What if you only had, you had 10 turns, 10, N equal 10 on the primary side. And you plug this into the wall, and that's 120 volts. Okay, you know that. Or 110, whatever. But we'll call it 120. 10 turns. But over here on the secondary side, you only have 1 turn. What's the ratio of that? 10 to 1, right? Guess what your voltage does? 120 to 12. The ratio of your turns equals the ratio of the voltage. However, if you had 120 coming in here, only had 1 turn, but had 10 turns on the secondary side, what have you done now? Step up the voltage by a factor of 10. Now you have 1200 volts going up. You don't want to do that in your house, okay? They may do that somewhere else, but not in your house. Okay. We did some outdoor lighting around our house, and the first thing we got was a box there that hummed a lot and stuff we plugged in, and that was your step-down transformer, because it stepped it down from 120 to something around 6 to 8. So that was a lot of turns on this side, very few on this side. Now, what is doing this? What is causing this to happen? What kind of current is this? AC, alternating current. And if it's alternating current, and you've got a coil here, then you're doing an alternating electric field. Now remember, with electromagnets, you didn't want alternating current, you want a direct current. But here we're going to use the same principle, but now the alternating current is producing an alternating magnetic field in here. And that alternating magnetic field is going through a loop over here, changing field creates current. But if you only have, now we're dealing with voltages here, 10 turns here to 1 turn there, we drop the voltage, 1 turn here to 10 turns here, steps up the voltage. So it's the same principle. Your coil here is an electromagnet, but it's a rapidly changing electromagnet, which rapidly changing current changes the field, changing field creates a current. That's the whole principle of electromagnetism in one illustration right there. Moving charge creates a field, changing field creates a current. In reality, it's all the fields. Everything's the field. Okay. Now, we finally hit an example. So let's do example 6.9. A step-up transformer has 5 loops in its primary coil. Which of these symbols now represents that? N sub P is 5 loops. I'm just going to put 5, okay? And 20 loops on the secondary coil. What would represent that? N sub S is 20 loops. Okay, I'll just put 20. Okay? If the primary coil is supplied with an alternating current, needs to be alternating, at 120 volts. So what would that be? V sub P is 120 volts. I'll put the units there. The question is, what is the voltage of the secondary coil? So what are we looking for? V sub S. That's the unknown. Set up your ratio like this. V sub P over N sub P, that would be 120. I don't have much room, so I'm going to leave off the formula. It's right there in front of you. Over N sub P, which is 5, is equal to V sub S, the unknown, so we'll just leave that V sub S over 20. Now, you can do the math here, and this is called, okay, these are called ratios. Remember, we did those in the first lab. Something divided by something is a ratio, okay? When you have one ratio equal to another ratio, that's called a proportion. To solve a proportion, the one way is to multiply these two by and set them equal to the product of those two. It's called the cross product. You cross across the equal sign. So this would be 5S is equal to 20 times 120. Now that's one way to do this, and we'll do it that way. 5V sub S is equal to 20 times 120 would be 2400, right? Then divide both sides by 5, and you get V sub S is equal to 480 volts. That's one way to do that. And that's really straightforward. That's how the book expects you to do it, I think. Okay? But let me show you a slightly easier way. When you have it set up like this, 120 volts is to 5 turns, as V sub S is to 20 turns. Why don't you do this? Just swap those two and do 20 is to 5 as V sub S is to 120. Because you're multiplying them anyway, it comes out the same thing. You can just flip those two. This gives you 4. So basically this says 4 is equal to Vs over 120, then multiply both sides by 120. And that gives you 480. Multiply by 120, and that gives you 480. That's just easier math that way. But you can do it either way you want to. Okay? 480 volts. It's a step-up transformer, and the key, what I was just doing here, since the ratio of the turns is 5 to 20, which is 1 to 4, the ratio of the voltage is 1 to 4. So you have 120 here times 4 would be 480. That, to me, is the easy way to do it. Okay? If they're weird numbers and not smooth numbers like that, then go on and do your division. It's just as easy. Okay.
It's 5:15.
Yeah, but we don't have a test today. We're going to 5:45. But do y'all want to take a break before then, or can you wait another half hour? Okay, keep going. Okay, let's do 6:10. Oh, wait. Yeah, wait. Okay. Before we do 6:10, there is another formula they give, they don't give on the slide sheet. Shame on them. Let me give it to you. Okay? When you're stepping up the voltage, which goes by the number of turns, coils, right? You're stepping down the current. So if you knew how much was coming in, now it's a inverse relationship. I don't usually use this formula, but you can't. Well, yeah, it works pretty nicely. Remember, power in equal power out. You can't create or destroy energy. And power is energy per unit time. Well, what is power in? Voltage in times current in. And what is power out? Voltage out times current out. So there you have another formula. Okay? Now, what they say is this. voltage on the primary side times current on the primary side equal voltage on the secondary side times current on the secondary side. However you want to name it, that's what it comes out being. So, the step-up transformer in example 6.9 is supplied with an alternating current at 120 volts. Okay? And 10 amps in the primary coil. So this would be 120 volts times 20. No, 10. 10.0 amps. And you figured from the last time what current flows in the secondary circuit. Well, you figured your voltage there. Did anyone remember what it was? We just did it. 480 volts times I sub S. We want to solve for that. So here's what we do. Let's divide both sides by 480. So I sub S is equal to 120 volts times 10 amps divided by 480 volts. Well, that's going to be pretty easy. The volts go out, and this we know is a ratio of 1 to 4. So it's 1/4 of 10, and what is 1/4 of 10? 10 divided by 4. 2.50, 3 significant digit, unit is amps. 2.5. Oh! How did they drop? Oh, I know how. When they said 120 volts, they didn't say that 0 was significant. So that's only 2 significant digits, so that's why they left off the 0. 2.5 amps. It doesn't matter. It's the same number. Okay. It's just the precision. All right. So know this. If you step up the voltage, you got to step down the current. If you step down the voltage, you're stepping up the current. So when you run into these, be sure that your answers make sense. Current has to drop if you got a step-up transformer. It has to increase if you got a step-down transformer. Okay. So we did 610. All right. This is the one I thought they were going to do earlier. And this is a neat little thing. If you have the time and patience to do it, it makes for a pretty interesting deal here. If you've can get a coil of wire, and basically you can run it around something like a paper towel tube or a toilet tissue tube or something like that. Run a coil of wire around it, just plain old copper wire, and suspend that from something so it hangs there and dangles, okay? And then run that same wire over here to another coil around, same type thing, another coil here, so it dangles, okay? Now underneath this one, put a magnet. They show a horseshoe magnet. Any kind of magnet will do. The horseshoe magnet has really strong field lines right there. And put it fairly close, but don't have it touching, okay? And then put another magnet, a similar magnet, right under that, okay? Now, there's no power to anything, is there? No current, no battery, you've not got it plugged in anywhere. And then what you do is get this one rocking. Back and forth like this. You know what's going to happen? This one's going to rock back and forth. Opposite blade maybe, but it'll still rock back and forth. You didn't do a thing to touch this one. You only started this one rocking, that one. Why? Rocking this one changes the field lines being cut by this coil, which creates a current in the loop. Now you have to have the current all the way, the loop all the way around, okay? And then that creates a current here, a changing current here. In the presence of the field lines, start this one moving, okay? And it looks like a perpetual motion machine, okay? You know that can't really happen. You have to start it rocking. But it will, well, it won't rock forever, but the other one will keep going as long as that one. They usually go out of phase, but still will work. Unless you turn the wires backwards. Okay. So, we're moving on to 6.6, which is circuit connections. Okay. Here we go. I almost lost my page. Okay. We actually did some of this in the first lab. Okay. Sorry we couldn't do all the labs after we had covered the material, but it wasn't bad to do the material lab first and then hit it with the material. So anyway, we'll go with this. And an alternating current is practically all generated electricity. In fact, in your car engine, you have a generator, okay? That's producing alternating current. But your car can't use alternating current, can it? Because everything else in your car is direct current. And why do you have the generator there anywhere? Wait, to recharge the battery, because you used it up when you started the car. And you need to replenish it, because it's a rechargeable battery. So what do you have to if you use just alternating current, that would charge, discharge, never get it anywhere. So what do you have in between? You used to have a split ring commutator, and that made it pulse DC current, so you could recharge your battery. Nowadays they use it's alternator, but what's in there? The alternator used to be a split ring commutator. Is it a dual diode?
Yeah, dual diode, rectifier, or something.
Yeah, something like that. Now it's electronic, it's not mechanical anymore. And I guess it's a little better and more efficient and more trustworthy and lasts longer.
Now they got them before you be going down the road, your battery stays fully charged, so it cuts off.
Oh, it does?
Yeah, the alternator cuts off, so you don't have very much of a strain on the engine.
Right. Does the generator quit? Does it shut down the generator? That is a good thing, a very good thing. Okay, so practically all generated electricity is alternating current, unless you have a split ring commutator, a dual diode, or something like that to change it to pulse DC. It's generated as alternating current. Transmitted over high voltage lines where you step up the voltage to get high voltage, you cut down on the current so you don't have the line loss. But then when you get to your homes or in town or somewhere like that, you step down the voltage, step up the current so you can use it better. Now, on the other hand, direct current is used in automobiles, cell phones, MP3 players, laptops, anything that has a battery, a flashlight, anything that has a battery, that's direct current. These need to be things that are movable, portable, that you don't have to be plugged into a wall somewhere. Okay, so those are going to be direct current. The main current source is your chemical batteries. It can sometimes be other things like solar cells or things like that, but it has to be something that produces direct current, like Volta's chemical batteries did. Now, here's what we didn't do in lab. Actually, you did do it, but you didn't. We didn't have the background for me to explain. Remember that first lab that we did in electricity, when we increased the voltage, that was like adding another battery. Okay? When I said double it, it's like going from one battery to two batteries. Okay? In that case, you hook the batteries plus to minus, plus to minus, plus to minus. Okay? That's called this batteries in series. This is a series circuit. What a series circuit is, the same charge goes through every line the same. Series. Same current flows through everything just the same. In this case, we've got your batteries in series. The negative terminal of one connected to the positive of the other. Now, they call these dry cells. They could be any kind of battery. But in most dry cells, they're usually about 1.5 volts, right? Your DC batteries, I think they're usually about 1.5, aren't they? Yeah. Okay? So if you had 3 in series and they're 1.5 each, that would be a total of 4.5. Okay, double it is 3, and another 1.5 is 4.5. So your total voltage is the sum of the single cell voltages. Now, if you had a 1.5 and a 9 volt, and then another 1.5, that would be 12 volts you just created there. So you could mix and match if you wanted to. Single current pathway, that's what makes this a series circuit. Single current pathway. Now, what would be the effect on the brightness of that light? First lap. As opposed to a single battery. Much brighter, exactly, because you have more voltage, same resistance, more current. More current, brighter light. Okay? Does that make sense? That's if your sources are in series. Okay? Your batteries. If, however, you're doing a parallel batteries, then you get plus to plus to plus and minus to minus to minus. What's your voltage across this? If these are all 1.5s, it's just 1.5. Everything's 1.5 across. Okay? So what would be the brightness of the bulb? Brighter or dimmer? It would be the same as if you only had one battery. What's the advantage then to putting them in parallel? Yes, they'll last longer. Now, if you were running a weather station up on top of Mount Cheeha, okay, I don't know if, I guess you can get up there. Do they run power lines up there? The top of Mount Cheeha, do you know? I've never been there. Let's just imagine they did. And you were trying to put a weather station up there. You didn't have a source of batteries, of power, so you had to use batteries. I would want as many in parallel as possible, so I wouldn't have to climb up there, but maybe once or twice a year, rather than having to do it every month. Okay? Lazy. Okay? You want it to last longer. All the negative terminals are connected, all the positive terminals are connected. Resultant voltage is the largest voltage you have in there. If this was a 1.5 plus 9 and a 1.5, that would be 9. Okay? Because the 9 overrides, but the 1.5s are contributing a little bit, But they'll last longer. It makes greater electrical. I don't like the way they word that. It makes electrical energy available for a greater amount of time. Okay? That's really the way to express it. Okay? It gives you, like you said, more amp hours. That's how you measure batteries, right? Amp hours. How long will it keep producing the charge? Okay? But your voltage stays the same. This is in parallel because now the earlier definition still works here. The same current flows through everything, but the thing is, these are not, in a sense, stepping up the voltages. They're keeping the voltage, if they're the same batteries, keeping the voltage constant, but giving you, basically, okay, what a battery is one plate and another plate separated, okay? Now, in your car, you actually have 4 sets of plates, I think, right? Or 6 sets of plates. And they're about 2 volts each, so it's a 12-volt battery, okay? So, and they are in series, because you're adding them up, okay? So, but basically, that's what a battery is, one plate and another. So this is like having bigger plates, okay? You just increase the size of your negative plate and your positive plate, so you have more battery life than you did otherwise. Okay. Oh, I didn't meant to turn the page. Okay. That was all the stuff. And by the way, at some dam somewhere, here's a bunch of transformers. And here I almost guarantee you these are step-up transformers. Whatever that electricity being produced by the hydroelectric dam is stepping up the voltage so you have less line loss. Because these are way out in the boonies somewhere. and they're shipping that electricity a long way. Here's your step-down transformer coming back in your house. All right, then there's a Science and Society. It's a rather strange place to put it, but it's okay. Basic. I guess y'all were alive, most of you, in 2003, right? Okay, but you weren't very old. Right. So you probably don't remember the fact that there was a huge electrical grid problem shutting down electricity throughout a lot of the Ohio Valley and massive electric power blackout affecting 50 million people in the U.S. You probably don't remember. We weren't involved. It was all up there, okay? And this is talking about some pollution studies they were able to do because of the blackout. So it's an interesting little blurb. It's a very small blurb, several questions. If you're interested in that kind of stuff, pollution, environment, that kind of stuff, it's a great article to read. Very short. Now, the next subtopic here is resistances in circuits. What we were doing here was voltage sources in circuits. Adding voltages in series increases the voltage. Adding them in parallel keeps the voltage the same but increases battery life. Okay? Resistances in circuits does something else. And this is what the other thing we did in lab. We did increase voltages, but this is resistances in circuit. This circuit is what kind? All the current flows through everything. So that would be series. Same current flows through every device. And the battery and every wire. Everything's the same. This is a series circuit. With one voltage source here, 3 lights, what would that be compared to the same voltage source with only 1 light? The dimness of the lights, or brightness of the lights.
It would be 3 times brighter than it was.
The one would. Okay, yeah, okay. I'm sorry. I keep thinking the Colt's better, and it keeps hanging in there. Yeah, if you put extra lights in a series circuit, they'll get dimmer and dimmer and dimmer because you only have so much source here, and you're splitting the voltage every time you put another light in. Okay, so that's sort of a disadvantage for a series circuit. Okay. By the way, y'all awake yet? Okay. Make sure you hadn't fallen asleep or anything. Okay. So, when you do this, what you're doing is adding these resistances. The voltage is the same current has to flow through everything, so you're adding resistances. With the voltage being the same, more resistors, what does that do to your current? Cuts the current. Because greater resistance, same voltage, your current has to be decreased. And that's why the lights go dimmer, because there's less current flowing through the circuit. So the current drops, the more elements are added. Now, the resistances are some of the components. Here's the other thing to add. If you put a voltmeter across here, well, if you put a voltmeter across here, that's the voltage of your battery. Let's just say 1.5. If you put it across here, that's the voltage drop. This is the voltage increase. This is the voltage drop across that resistor. And if these are equal light bulbs, that would be 0.5, 0.5, 0.5. Total drop of 1.5, total increase of 1.5. So a series circuit splits the voltage, keeps the current the same, though it drops every time you add another one on, adds the resistors. Okay? So the current drops, the more elements are added, total resistance is sum of all the components. Here's the formula for that. Pretty nifty, somewhere here, formula. R total is R1 plus R2 plus R3 plus as many as you have in the circuit. That's your total resistance. Sorry. Okay. All right. Now, pretty simple formula too, right? Now, what about resistors in parallel? What would that look like? Here they are. Here's your battery here, your voltage supply, your potential difference. It's the same here as it is here because that's connected here, that's connected here, as it is here, as it is there. Same voltage drop. Okay? Now, what happens to the current though? Some of it goes here, some of it goes there, and some of it goes there. And then they come back in, combine, and combine, and come back. Okay? What you have there is the splitting of the current, but the voltage stays the same. Whereas in a series circuit, the current was the same, the voltage was split. Okay? Now, what's happening with the resistance? If you have the same voltage here, but then every time you add another resistor, same voltage, and if it's the same resistance, then you're demanding the same current, right? Ohm's law, okay? So you just got more current. So every time you add a resistor, your battery's having to supply more current. So the battery feels like your resistance is getting less because it's having to supply more current. That's the weird thing about adding resistors in parallel. It actually decreases the overall resistance of the circuit. Weird. Adding more resistors in parallel decreases the total resistance of the circuit. Now, here's the deal with parallel connections. More than one current path is available. Current can go here, here, or here. So therefore, same voltage, it demands the same current with the same resistors. So that's more and more currents having to be produced. The overall resistance drops as more elements are added. That's what I was just telling you. The total circuit current increases as you add more. So that's why plug too many things into your outlets, have too many drop cords and stuff, blow a circuit breaker, right? Because you're demanding more and more current. After a while, it says, look, this is all the current you allow, I'm going to pop. And it does. Okay. Uh-oh. There it is. Here is the formula for your resistance in parallel circuits. It's a reciprocal relationship. 1 over your R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and on and on and on. And every time you add another one here, this one gets less. In fact, the overall resistance of your circuit, I like to call it effective resistance. The book calls it total resistance. To me, total means greater. Effective doesn't necessarily mean that. It has to be less than any single resistance in the system. Has to be less than any single resistance in the system. Okay. Now, the question is, do we have time to do 611? I think we do. So let's try it. Okay. 3 resistors with resistances of 12 ohms, 8 ohms, and 24 ohms are in a series circuit with a 12-volt battery. Series circuit. So here's your 12-volt battery. I won't draw all the things, okay? Here's the plus side, and here you have a resistor. Here you have a resistor, and here you have a resistor, okay, coming back into the battery. You can draw them any way you want to, just make sure it's a series circuit, one pathway, okay? This is a 12 ohm resistor. This is an 8 ohm resistor. and this is a 24 ohm resistor. Okay? This is a 12 volt battery. Okay? What is the total resistance of the resistors? Not that hard to do. What would it be? R total, or effective, whichever you want to call it. Can you do that, anybody? Pretty easy math. Say again? 44, isn't it? 44 ohms. I'm doing it quickly in my head. 8 and 12 is 20, and 24 is 44, right? Right? Okay. 44 ohm resistor. Okay? That's question A. Question B, how much current can move through the circuit? So what's your I? Give it. V divided by R. Good old Ohm's law there, right? And the voltage is 12 volts. And the current, the resistance, total resistance is 44 ohms. And I'll need a calculator on this one. What's that? 12 divided by 44. 0.27. And that would be what unit? Amps. Current's measured in amps. Okay. Now, the C question is, this was A, this was B, and what's the C? C says, how much current goes through each resistor? The same. That would be 0.27, 0.27, and 0 amps, and 0.27 amps. It's got to be the same. It's a series circuit. Everything goes through the same pathway. Okay. Now the question they didn't ask is what's the voltage drop across each resistor? What would it be across this? I don't have a calculator, so I can't do it in my head, but it's 0.27 times 1.2. 0.27 times 1.2. Something just a little bit greater than 0.3.
Wait, what did you say?
1.2 times 0.27.
Yeah, 0.324.
0.324. So that's the voltage drop. Delta V is 0.324. What's the voltage drop across that one? Eight times 0.27.
8 or 0.8?
8 times 0.27.
2.16.
Wait. What did you do on the last one? Oh, wait. I'm sorry. I read that to be a 1.2. That's the 12. I'm sorry. That dot on the board messed me up. So go back and do 12 times 0.27. That would have been 3 point something, right? 3.24. Okay, sorry about that. 3.24. And this one would have been 2.16 volts. And this one would be 6.48 volts. That's delta V3. Now, quickly add 3.24, 2.16 plus 6.48.
11.88.
Okay. You had some round off error. That's all it counted for. That's your 12 volts back. You just had round off error. Okay? Now, that was example 611. All right. Before we go to 612, there's a blurb on solar cells. Now, this is a much bigger blurb. Okay? And this gives a lot more information. Your junctions between N silicon and P silicon and that kind of stuff. It basically is how solar cells work. And these create DC current, okay? Has to be DC, unfortunately, okay? It's just sort of like you're forcing a battery, but not quite that way, but something like that. So anyway, nice little blurb if you can read it, okay? Might be a paper topic or two in there. Hint, hint, okay. Now, example 612, we don't have time for it, do we? We're already over. Okay, we'll start there next time. By the way, did someone leave a really nice pencil in here the other day? I found one on the floor. I don't remember if it was yesterday or it's up here in the drawer if you need it. Huh? Okay, we'll start at 612 next time. So, two things before anyone disperses. Let me call roll again. Logan's still here. Jay's mostly here. Ethan's mostly here. Amanda, I think, is here. Jonah, Patrick, and Thomas are here. Latricia did not make it in today. Frank is still here, mostly. Mendez is here. Mark is here. Diamond's here. And even Ron's here. I'm sorry. All right. Let's pause. Okay. Each of you have, or not all of you, several of you have a metal, and Jay here has a magnet. So I want to see how y'all attract each other. Who's aluminum? Okay, aluminum. See if Jay is attracted to you. What you say? No. Okay, no for aluminum. Copper. Copper guy. That's a great conductor. What you think? Okay. Maybe he's not very magnetic. Okay, iron. Who's iron? Okay, there's iron. Oh! Okay, so he is a magnet. Okay, how about lead? Looks a lot like iron. What you think?
Yeah.
So what? What'd you say?
Yeah,
It's got some magnetism.
Really?
It's just the waves in it.
No. No. Okay. Maybe we need another magnet person. No, okay. Nickel.
It is.
Yep. Okay, nickel, yes. Tin. Looks a lot like. Nope. How about zinc? No. Okay. I didn't bring in any plastic, wood, or styrofoam. I thought, no, that's a use. What you think? You can either leave those blank. Hey, look at that.
Science, you always have to run your test.
Huh? Yeah.
Science, you always have to run your test.
Before you know, huh?
Put us on the wood.
Okay. The drawers are fake wood. You can try them on that. No, I'm just kidding. Okay. Now, why don't I have my glasses on? All right, now things are a lot clearer. Up close, anyway. Okay. I need 2 holders of pens. Who hasn't held something?
We're excited.
Frank,
Oh, you held something. Oh, okay. Here's another. Okay, here's a pen. That's a needle, actually, but it's okay. Okay. Now, the question here is several pens have been, well, one of those was in styrofoam, but it came out, but it's okay. Test one to see if it's magnetized by touching its point into a, no. Yeah. I want you to do it. To point into the iron filings. What do you see? Everybody see this? Come on up so you can see. Yeah, stick it on in there. Okay. Yeah, that's, see the iron filing sticking all over it? They're standing up on it, following the field lines. Okay? Now, that's the point. Turn it over and see if the head's magnetized. Whoa, I would say so, wouldn't you?
Yeah.
Okay, everybody see that? All right. Now, what we want to do, it says in water, we're not going to do it in water. Set it down on the table and Magnet Man come over here and see if you can figure out which is the north end and which is the south end. Whoa! What do you say?
I'm gonna say that's.
Wait a minute.
Change it. It attracts both ways.
Well, okay. This is strange.
Well, now I'm broken.
This is totally weird.
Flip it over, I think. No, it's the same lettering.
Oh, there we go. Now that makes sense.
I sound
Okay.
pretty.
I don't know.
Everything you touch. It was a trick.
What's going
I
on?
made a new design.
Okay. All right.
I think you mean about
This is.
You can't make it mine.
Okay. I think this is too strong a magnet. It's overpowering this one. Let's get the compass. I think that'll do that. Well, first, let's check this again and make sure it's still magnetized. Okay?
Right here.
All right.
Do it. Come on.
Stick it in.
Stick it in there again. Make sure we didn't destroy the magnetism. Is it still magnetized? Oh, yeah.
Try the other way.
Yeah, probably. Make sure it's still in. Okay, now, this is a much weaker magnet here. Let's see if I can line it up. Okay, so bring it over here and bring either point or head near the north and see what happens.
It repels.
It seems like it's repelling. Do the other side. Move it some.
Did a track.
That's the track. Okay? Now, we'll have to swap positions. Okay? Move it some. That's attracting the point and repelling the head. The south is being repelled. Right? So, which is the north, which is the south of the pin?
The north is the head, and then the south is the point.
Okay? Because the north, nope,
And the head would be south.
head is south.
Yeah, the
Head is south because the,
The north.
see, this is repelling. This is attracting. Yeah.
Why you running on paper?
All right. All right. What was happening before, that was such a powerful magnet, it was overpowering the magnetic field of this one. We did get it to do a little bit, but not great. Okay. So, now, everybody get that one? That was, let's see if we can find a pin that's not magnetized. Who had my needle? Okay? Stick that in and see what happens. Oh. Okay. It's just slightly magnetized. See, not much comes out. Okay? Do the other end. Just make sure the head isn't magnetized either.
I have before us.
Very weakly at all. So, we found a pin that was not magnetized. That's number 2. Okay? Now, magnet.
Yes.
Go, stroke. Now, let's read the instructions. Okay. We tested it. Now touch the head. Wait, sorry, okay. Magnetize it by stroking it, its point on a magnet. Take the point of the needle and stroke it on the magnet. Okay, toward the end, for one of the ends, one of the poles. Yeah. Okay. All right, that should do it. All right. Now you only stroke the point, though, didn't you? You take the point and put it in the pilot. What would you say?
Yes.
Uh-oh. Okay, I'll hold this if you need it right.
So, I tested my
Yeah, but we haven't gotten anything. So we did increase the magnetism of the point, right? Now, you didn't stroke the head though, did you?
So,
You did?
I get
No. Okay, well you try the head and see if it's magnetized. It was magnetic before,
like Magneto.
Okay. Let's see what happens. Put it
Never
in.
watched it.
Oh! How did the head get magnetized if he only stroked the point?
You magnetize one end of the pole, and make the other pole.
Okay? Magnets are always what? Two poles, dipoles. Magnets are always dipoles.
So, yes.
Okay? So the number 2 was a yes, because the head magnetized as well as the point, and neither one were very strong to begin with. Okay. Number 2, the only question is, did you increase the magnetism of the head as well?
Yes.
Yes. Okay. Number 3, if yes, then explain how you increase the magnetism of the head by stroking only the point.
A magnet has two.
Yeah, magnets are always dipoles. So if you make one end one, you automatically make the other end the other. So let me get my needle back. I don't want to look at my haystack for it.
Same.
All right.
I mean, it sticks up a little bit.
Yeah, that man.
Usually before this lab, I have to go to all the pins and all the needles I've had over all the years trying to find one that's lost its magnetism because we've done it so many times. They're all pretty much magnetized. But this time on Veterans Day, they gave me a ribbon with a needle on it. I said, I'm not returning the needle. I know where it's going. So we've used it now. In future years, I got to get another pin somewhere. All right. Now, what we need to do, I'm sorry, I went too soon. Y'all remember what the magnetism was of your first one, right? Did y'all write it down? Okay. What we need to do is determine which pole is which of the needle. So whoever wants to do it can do it. Hey, not that one.
Oh, not this.
Yeah.
You have to do it.
No, with that. You recorded it for that needle, didn't you? Okay. Someone get close and see. Okay, it looks like.
Oh, the new man.
Yeah, the new magnet.
So, head and head.
So the heads are the same. See if the points are the same. Yeah, repelling there too. Okay? So whatever your head was before, which was north-seeking before? The point. So they're the same on this one. So the point is still, what's the question? How does it ask? Yeah, north-seeking, south-seeking. And you told that by comparing it. We could have compared it with the compass as well, but since we had that one, we're only using it. And again, that big old hunker of a magnet here, that's overpowering anything.
Super, it's a Superman.
Okay. Now, we're going on a field trip. Okay? Who's going to be holder of the compass? Who hasn't held something yet? Okay? Holder of the compass. Okay, we're going down to room, I think, 261. Unless there's a class in there, if it's a class, we'll go somewhere else. Take the papers with you. Yeah, I know, but that's changed, yeah. It's moved around each day.
Huh?
Okay? We're not going to 265, so stay inside of me so you don't go to the wrong room. Bring your lab, bring something to write with.
You don't need to be like that guy. Oh, baby, you don't need to
That's so crazy.
Okay, this is definitely going to be a team effort now. Okay?
This is team building. Spell team. Spell stall. T-E-E-N. You.
I mean, you call twice.
Stall. You are
That's
among
only
them.
one. That's all I'm getting.
I've been going over it.
Tell me it's not word. He's like, I died.
You said, I said, you are.
Not yet, not yet. We already had one baby-related death in Alabama. You can't be no, I had one.
I'll get.
We only have one. I'm pretty sure.
You're
I mean, I'm not gonna stop you.
Sorry, folks. Now, we've got page 1 done. We're on page 2, getting close to the center of the page. Here's our Toyota electromagnetism master. Okay? Y'all gather around. You need to see this. All right. Now, here's their station 1. I've got red to red, though I don't have this one plugged in yet. Well, I could go and plug it in. I'm not. Wait. And black to black. Okay? Now, what we're going to do is, with our compass here, we're going to see if we can deflect the compass needle at all. Right now, the south is closest to this, the left end here. We're going to see if we can deflect it. We're going to have to, it says 1.5 volts. Most of the time it won't work, but we're going to start there, and then we'll increase it slowly and see what happens. So I'm going to start off at 1.5 volts. This is my drifter. Okay, it's 1.6. It doesn't matter. Okay. Now, when I touch this, you let me know if you see it deflect. Touch? No. Okay. Now it changed again. Let's go up to
24 volts.
all right, 2.5. See if it deflects at all. Touch? Okay. We'll go up to 4.1. Touch? Not a bit? Okay. Let's go up to, part of this is the power supply is drifting like crazy. Now we're at 6. Okay? Touch?
Nope.
Not a bit of deflection.
Nope.
Wow. Okay. 7. Touch?
No.
Not a bit.
No.
Let me try it this way.
You gotta open in the circuit.
Yeah, this is okay. Touch?
There we go.
Oh, okay. This was a bad connection here. Okay, what is the South Pole doing when I touch? Touch?
Going away.
Okay,
So
so it deflected away. So, what happens to the compass needle? The south-seeking pole moves away from the left end of the coil. You got it? Bring your paper down here so you don't have so far to walk. Okay? South-seeking point of the compass moved away from the left-hand end of the coil. Okay? So, which would be the north pole of the coil? Okay? It would have to be the right, because this must be a south pole because it deflected it, moved it away. So the right would be that. You got it. All right. Now what I'm going to do now is reverse my polarity. Okay? Keeping the voltage about the same. Okay? And y'all pay attention to what happens to the south end of the magnet, of the compass. Are you watching? Touch. Goes toward, okay. So, touch the, okay. Are there changes? Yes. These, yeah, exactly. Flip the polarity of the, and this is basically a solenoid, is basically what that is. A coil of wires with direct current running through it. Okay. Now, we're going to station B. Okay. I'm going to move my wires back to red and black to black. All right. At station B, plug the wires according to the colors. Now this time we're going to do something else. We're going to plug the yellow wires into the micro ammeter. Now this is where a lot of coordination is going to have to come into play here. Okay? Now, one person, I'm going to crank this up to 9 volts when I get started. I'm going to turn it off for now. I'm going to crank it up to 9 volts. Okay? And we may have to crank it higher, but we're going to start with 9. Okay? And what I want someone to do, someone is going to pay attention to these 2 lights here. There's a red light and a green light. Green light's here, red light's here. They're both off. So someone come do that. Okay? And someone else is going to pay attention to the micro ammeter. The trouble is, the lights are so dim with these lights on, we got to do this in the dark. So the dark is going to be for the light detection. We have to turn the lights on again. You hear that? On again when we're doing the ammeter. So we're going to do the same thing probably several times over. Okay? Okay. Oh, he's got a flash on. Okay, but all right. Now, wait a minute. I got to read the paper. Okay. All right. So what I'm going to do, I'm going to do the plugging, and I'm going to announce. Okay. Lights. Connect. Disconnect. Did you see any light come on? Okay. Turn on the lights for me. Oh, I turned off the power. Okay. Let me crank this up to 9. Going the wrong way. Okay, there's no coughing in here.
Oh.
Both of you understand. We both coughed in the restroom during the pre-cal test, Dr. Fowler.
All right. It's up to 11 volts. I couldn't get it to settle out at 9. Okay, lights. Okay, touch. Disconnect. You see a light?
Do it again.
Okay, turn off your flashlight for a moment, if you would, please.
I was looking at the
Okay, turn on the light again. Okay. Yeah, the light's right under that connector. Okay, lights. Connect. Disconnect.
It's in a red when you connect it and the green when you disconnect.
Okay, turn on the lights. Red on connection. Don't put anything for disconnect yet. Oh, go down to 5 and do that. Number 5, what you say, green on disconnect?
Yeah.
Okay, red on connect. On number 4, green on disconnect. Okay? That's number, yeah. Number 4 is red on connection. Number 5 is green on disconnection. Everybody got it? Okay. Now we'll leave the lights on and let Mark tell me if he sees the micro ammeter move at all. Look carefully. Okay? Connect.
Barely.
Which way?
To the right?
To the right. That's positive?
Yes.
Okay? Disconnect.
Back to,
Went back. Did it go negative? Okay. So, you got that now. It went positive on connection. That's number 4. And negative on disconnect. That's number 5. Okay. By the way, we're up to 11.4 volts, by the way. You might want to note that rather than 9 volt. 11.4. And he just barely saw the, Logan, would you say those lights were bright or pretty dim?
They're pretty damn.
Pretty dim. And the ammeter just barely moved, right? So this is just a note.
How many volts? 11?
Oh, my knee. Okay. All right. Now, I'm going to reverse polarity here. Okay. And now we're going to do it again. Everybody got 4 and 5 done, right?
Yes.
Okay. Now 6 is at the bottom of one page, 7 at the top of the next one. So it's connect to disconnect again. So lights, connect, disconnect. Lights on. Did you see any light?
I seen the lights. Yeah, they seem brighter.
Okay, yeah, but tell me what light you saw on connect and disconnect. Turn it off. Connect. Disconnect.
I think green on connect.
Green on connect, red on disconnect. Is that right? Okay. So number 6, green on connect, and number 7 on the next page, red on disconnect. Is that what you said? Okay. Is that reversal what we had before?
Yes.
Okay, good. All right, we're going to do the same thing with the ammeter. You can leave the lights on now, but we're going to wait. It's still at 11.3 volts.
All right, let's go.
All right. Connect. That was negative. Disconnect. Positive. Okay. Everybody get it? When I reverse the wire, number 6, negative on connect. Number 7, positive on disconnect. Now, either one of them. Did the light stay on or did the ammeter stay positive or negative once it was plugged in? No, they only moved when I was connecting and disconnecting. Okay? That's the key thing. Okay. Now, here's why. It takes a changing current to, okay, all right, wait. Before we do that, come here and look at the thing here. Yeah, what was the question? Okay, we're on number 8. Explain the observations. Here, look at what we're doing. I was sending the power through this coil. Okay? These are connected to this coil. They're not connected. The coils are not. They're not connected. Okay? So what we were doing when we had a changing current in this one, that produced a changing magnetic field because this is a solenoid, right? Well, the changing magnetic field here created a current here, and that's what made the lights come on and this microammeter move. Otherwise, they wouldn't have. So we were creating a current here by changing a magnetic field here. But it was only a changing current that created a changing magnetic field, only a changing magnetic field that created a changing current here. So that's what was happening. Now, you have this little space, but basically, write down what you got. And by the way, flipping the wires, reverse the polarity.
So changing current created change in.
A changing current created a changing magnetic field, and that created, in the second coil, a changing current. A current. Okay. Only a changing magnetic field creates a current. Okay. All right.
Changing current, magnetic field changes the current.
Changing current.
Only a changing current creates a magnetic field, and only a changing magnetic field creates an electric current. Okay.
So if you swap these around,
Yeah.
these and those, is that a step up or a step down?
Okay.
Since there's two different size pools, I was just wondering if it would make a difference in
Okay.
the voltage or the amperage.
This isn't quite a transformer.
So So it's not.
because the transformer has that core that connects them.
Mhm.
And so, but this is just basically inductance, changing magnetic field, inducing a current. And that's what we're showing. Now, we're moving now to station 5. I've moved these, and I'm going to move these. Okay? Now,
Would this be like a transformer?
no,
No,
not
it's
quite.
still not the same.
Yeah, we don't have a transformer set up here. Okay? Now, do you notice any differences here?
There's only one.
The input is now inside the output. They're not touching still, they're not connected. See, this is completely separately wired from that one. Okay? Completely. Okay? So, what we're going to do, and this time I'm going to start down at 1.5 volts. Okay? Not 11. Now 1.5 probably won't work, but we're going to start down there. Or somewhere close to it. So we got much less voltage. Okay. Went way below. Okay, we're going to start at 2.3. Okay? Is my white man in place? Okay, pay attention to lights. Connect. Disconnect. Did you see any lights?
I do. Again, I didn't see it.
Okay, wait, well, turn it on again. Okay. Okay, turn it off. Connect. Disconnect.
I didn't see
Nothing.
it.
Okay. I'm going to crank up the voltage to 3.9. Okay. Okay. Lights. Connect. Disconnect.
Red on connect and green on disconnect.
Red on connect, green on disconnect. And that was actually at 2.3 volts. You can note that. Okay.
You said red on connect.
Red on connect, green on disconnect. Now this is number 10. This is number, no, I'm sorry, you're not. It's 9. And we're putting everything on one line here.
Okay.
I got, okay, red on connect, green on disconnect. All on number 9.
Okay.
Okay? Now, with lights on, you get it? Okay, look at the microammeter. Connect, disconnect.
Disconnect to the right.
Connect
To the left.
to the left. Okay? So connect with positive. Is that right?
Connect is negative.
Oh, wait. Do I have them wired backwards? I shouldn't. Okay, let's try that again. Connect,
Move to the left. Negative.
disconnect.
To the right.
Right, I may have. Okay. I don't know what happened. Okay. It's fine, whatever it is. And by the way, that's down at 1.1 volts now. Okay, was there more or less deflection we had before? About the same? Okay. Your lights, were they brighter or different? About the same.
Seem to be about the same.
Okay, but much less voltage. Now we're down to 1.1. I'm going to move up to at least 1.5. Whoa. Or 4, okay. This is weird. Okay, I'm going to swap polarity. Okay. Now, we're going to switch wires. We're at 4.1 now. And I'm going to touch red to black, so we change. So lights.
Lights.
Okay, you ready?
Camera.
Connect. Disconnect. Got it?
Green on connect, red on disconnect.
Green on connect, red on disconnect.
I like it moved the wires when you did that.
Alright,
That's
which
weird.
one is this?
What's that?
I felt like it moved the wires when you did that.
11.
Me too. I'm gonna say, whoa. Timing
Okay.
over here.
So red on connect.
Is that
No,
what you
green
said?
on connect.
Oh, was it green?
Red on disconnect.
Yeah, green on connect.
I can't read.
All right.
What was the voltage?
Now, microammeter, We're down to 1.3 volts. I think that's one of the reasons we had a problem before. The voltage had dropped. Okay, we're back up. Okay, we're at 3.5. Connect,
To the right, positive.
disconnect.
Then do nothing on this one.
Well, that's because the
Oh.
voltage dropped again. Let me do it, okay? About 3.6. Connect,
Right. Negative.
disconnect.
Nothing.
Oh, you lost your voltage again.
Oh, I did. Look at that. Every time I do that, it drops.
Maybe not. Hold it or something. Like it's through.
Okay. 3.4. Connect,
Connect to the left, negative.
disconnect.
Right, positive.
Okay.
It's the same as the first.
Okay. Now, would you say, and was that more or less deflection than before?
More.
More deflection than the previous one. Okay? Now, even though the voltage was less than half, we're at 4.6. I didn't want to be that high, but that's what it drifted to. Whereas before we were 11, all right? Okay. So question number 11, why were the responses greater at station C, this one, than they were at B, this one?
Because it's connected. Inside.
Okay, the coil was inside. Now what difference does that make?
With a different magnetic field.
Yeah.
Okay, more field lines are being cut. In fact, all the field lines are being cut here. Here, the only field lines being cut are those near the ends. Now, inside there, all the field lines are being cut by this other one. So therefore, the greater number of field lines, the greater the response.
So,
Number 11, because the input coil was inside the output coil, so more field lines were cut. Many more field lines were cut. Okay. We're moving to station F. Now we don't need the lights anymore, so you can come back and join the rest of us. Your probationary period is over with. Did you bring your pointed hat? Never mind. Huh? Okay. Now, someone explain to me what station F is.
grade that I don't want.
Okay. Okay. Here we have a magnet that's labeled N, so I assume the field lines are pointing down. Under there we have another magnet, and that's probably an S, so the field lines are pointing down. Very strong direct field lines, fixed in place. Everybody see that? Come on over so you can see it. Okay? North magnetic field going down, south magnetic field also going down. Very strong field lines, fairly close to parallel, going through. Now inside this is a coil, and we're going to spin the coil. So what we're doing when we spin the coil are changing the number of field lines being cut by the coil. Maximum being cut there, minimum being cut there. Max, min. But they're changing in different directions. Here it's decreasing, increasing, decreasing. But it's that's the setup. This is like a little generator. Okay? So this is number which? Station F, number 12. Okay. Someone turn the coil clockwise and the others read the ammeter. I'll turn it because I know how fast you have to turn. Look at the ammeter and see what happens. Not at all. Okay, let's make sure.
Is it on?
There's no on or off.
Oh.
In fact, I need that's off. Okay. Turn this all the way down. Okay. Not moving at all?
Turn it on.
It's trying.
Yeah, but what's it doing?
Positive. It's trying.
Moving slightly positive, but it doesn't. It's not very steady. Okay, but slightly positive. Okay? That's number 12. Okay? I'm going to reverse the polarity of these two yellows. Okay? Now I'm going to turn it again. Notice what happens. Moving slightly negative.
Is that 13?
That's 13. Oh, wait, I'm sorry. I should have left the same. I didn't read the problem. This time I'm going to spin it counterclockwise, not clockwise. Moving negative. Okay, that's 13, moving negative. Right answer to the wrong question. Okay, now I'm going to reverse the wires. This is number 14. Okay, and I'm going to turn it first clockwise, negative, counterclockwise, positive. Why, if this is a generator, isn't it alternating? It's either positive or negative. So come and look closely, folks. Oh yeah, write your answers first. Okay. 14, we haven't answered 14 yet. You just made the observation. Okay. What type of connection does this have? Notice this. Here's a brush on this side, a brush on this side. But what's in the middle? There's a break, and there's a break. That's called a split ring commutator, exactly. This is a split ring commutator. Because as soon as it would go negative, it flips the polarity here with a split ring. Then they reverse. Okay? So the answer, what kind of connection does the coil have? A split ring commutator. Now that's a very small line to put that big old 3 words on. And what's the result of that? In the class today, we gave it a name, a direct current generator. It is a generator, but because of the commutator, it only does one direction. Either positive or negative, depending on which way I spun or which connection we had. The other thing you might want to say about that is it was a pulsed direct current, DC, pulsed DC current, DC circuit or whatever, generator. Okay. Now we're moving to G. G whiz. Okay. Now someone describe what's happening in G. Fixed on the outside we have
The coils.
coils, but on the inside we have a magnet that is spinning. Do you think this is going to make any difference? Whether the coil spins and the magnet's fixed, or the magnet spins and the coils are fixed?
Yes.
Doesn't really matter. Okay, but this one doesn't have a split ring commutator. That's the only difference. And that's the only thing that's going to make a difference. Because if you read the ammeter when I turn this, positive, negative, positive, negative, positive, negative, right? You have true alternating current here. Okay? At station G, connect the 2 yellow lines from terminals 8 to 11. That's what we did. Turn the magnets inside the coil, record the response of the ammeter, positive and negative.
So true alternating current?
That's true alternating current. Number 16, what was the difference between F and G? Now sure, what was spinning was different, but that didn't make any difference in the current.
The type of commutator.
It's the type, yeah, that you had a commutator on F, but you did not have one on G. Does that make sense?
Changes polarity right there.
I know.
is 21st.
Did I? Oh no, I had the recorder on. Good deal. I hope it picked it up. Let me turn. Yeah,